What we call the Big Bang is not an explosion in space. It is space itself changing and carrying everything with it. Yet the moment we try to push past that boundary, our language turns treacherous, because words like cause, origin, and even start quietly assume a clock already running. This documentary is a guided descent through the evidence and the limits of evidence, where each step backward is paid for with harder questions. We will treat the universe like a crime scene, reading its expansion in the stretched signatures of galaxies and its afterglow in a nearly perfect microwave blackbody that still fills the sky. We will watch simple atoms become testimony, as hydrogen and helium ratios preserve the first minutes like a chemical timestamp. Then the trail narrows to the first fractions of a second, where the cosmos may have grown faster than intuition can hold. An episode proposed to explain why the heavens look so eerily uniform, and why tiny quantum jitters became the scaffolding of everything that followed. But as we approach the Planck scale, our best theories stop acting like maps and start acting like warning labels. General relativity and quantum physics both insist on speaking, and they do not yet agree. Here, singularity is not a destination. It is a sign that a model has been pushed beyond its jurisdiction. And nothing is not a simple emptiness, not the clean philosophical void we imagine in the dark, but a word with competing meanings, some of them disturbingly structured. In one sense, it can mean a quantum vacuum, a lowest energy state that still seethes with fluctuations. In another, it can mean the absence of classical space-time, where even the stage of reality is no longer guaranteed. So we will ask what physics is allowed to say, and what it must refuse to pretend it knows. Could the hot beginning be a transition rather than an absolute birth, an aftermath of a bounce, a collision, a phase change, or a deeper process that makes time itself an emergent feature? Or does the very demand for a before collapse under scrutiny, like a question asked north of the North Pole? To answer responsibly, we will not chase comfort, we will chase consequences. We will follow predictions into the microwave sky, into the distribution of galaxies, into polarization patterns and gravitational wave whispers that may or may not exist. And we will see why the most honest frontier in cosmology is not certainty, but constraint, narrowing the space of possible stories until only those that face observation can survive. Because the stakes are not merely academic. If the universe can arise from what science calls nothing, then nothing is not what we thought it was. And if the beginning of time is not the beginning of reality, then our deepest intuitions about cause and creation must be rebuilt, carefully, mathematically, and with humility. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 7 chapters, we move from hard forensic clues to the edge where equations fracture, and into the bold proposals that try to replace that fracture with history. By the end, you will know what the Big Bang explains with confidence, and exactly where the mystery still resists us. Imagine rewinding reality, not on a screen, but in the laws that hold it together. The image is cinematic, frames snapping backward. Yet the thing we reverse is not footage. It is cause and effect, written into space-time itself. We run the film backward past cities, past Earth, past the first stars. Streetlights dim into continental outlines, continents blur into cloud bands, and cloud bands dissolve into a young planet still cooling. We keep rewinding until even the stage itself begins to vanish, as if the projector were eating its own screen. The idea that waits at the end is seductive. Absolute nothing. No matter, no light, no space, no time, no rules, no observer. A blank that should stay blank because there is nothing to disturb it. But the first problem is language, and it arrives immediately. Nothing is a word built inside a universe that already exists, so it smuggles in assumptions. The moment we try to describe the absence of space and time, we borrow metaphors from space and time. Even our grammar leans on a stage. We say before, outside, and where, as if there were a calendar and a map. When the subject is the birth of the map itself, those words start to wobble. Cosmology begins with a simple confidence. The universe has a history, and that history leaves traces. If we can read those traces, we can run the story backward with increasing precision, like reconstructing a shattered vase from its matching shards. We do this every time we look up. Light is a time machine because it takes time to cross distance. A galaxy a billion light-years away is seen as it was a billion years ago, not as it is now. As telescopes push deeper, the sky becomes a layered archive. Nearby galaxies show mature spirals and settled clusters, while distant ones look smaller, bluer, and more chaotic. The farther we look, the more we approach an era when structure had not yet fully assembled. The farther we look, the more uniform the cosmos appears. Galaxies thin out into a smoother glow, and structure gives way to a simpler state. That simplicity is not emptiness. It is density and heat, matter and radiation packed so tightly that the universe behaves like a furnace. This is where the Big Bang enters, and where misconceptions begin. The Big Bang was not a bomb exploding into pre-existing darkness. It was not matter rushing outward through empty space, leaving a central crater behind. The Big Bang is our name for an early hot, dense phase, when space itself expanded. Distances grew because the metric of space-time changed, which is the technical way of saying the ruler of the universe stretched. Everything was once closer, because the ruler of space was different. That distinction matters because it changes the picture in your mind. Expansion is not a blast wave moving through a room. Expansion is the room's geometry changing, so every separation grows even if nothing is pushing through a background. If space expands, then center becomes a misleading idea. Every observer sees distant galaxies receding because the expansion is built into the geometry. The Big Bang happened everywhere, not at one point, because everywhere is what was expanding. This is not a philosophical preference. It is tied to measurements that can be checked, repeated, and refined. The universe is not only old in our equations, it is old in our data, and the data come from multiple directions. The first anchor is cosmic expansion. In the 1920s, Edwin Hubble and Georges Lemaitre connected redshift to distance, building on earlier hints from Vesto Slipher's spectral measurements. The farther a galaxy is, the faster it appears to recede, and the pattern is strikingly systematic. That relation, now called the Hubble-Lemaitre law, is not about galaxies flying through space like shrapnel. It is about space stretching the light on its way to us, lengthening wavelengths as they travel. Redshift becomes a record of expansion, written directly into the spectrum. When astronomers measure that spectrum, they see familiar atomic fingerprints shifted toward longer wavelengths. Those shifted lines act like tick marks on the cosmic ruler, letting us estimate how much the universe has stretched since the light began its journey. The measurement is humble, just light through a prism, yet the implication is enormous. Run that expansion backward, and the average density rises. Temperatures climb because radiation is compressed, and particle energies increase. The universe becomes a plasma where atoms cannot hold together because energetic photons tear electrons away as fast as they try to settle. In that plasma era, the cosmos is not transparent. It is more like the interior of a star, where light does not stream freely but ricochets, scattering from charged particles again and again. The universe is bright in principle, yet opaque in practice. The second anchor is the cosmic microwave background. In 1965, Arno Penzias and Robert Wilson found a faint microwave hiss from every direction while testing a horn antenna, and the signal refused to disappear. It was not a local signal. It was cosmic, and it sounded, on their instruments, like a persistent, featureless whisper. The CMB is relic light from a time when the universe first became transparent. Before that moment, photons scattered constantly off free electrons in the hot plasma. After that moment, electrons combined with nuclei to form neutral atoms, and light could finally travel long distances without being deflected. This transition is called recombination, though it is really the first stable combination. It occurred when the universe cooled to a few thousand degrees, roughly 380,000 years after the hot beginning. The number sounds large, yet in cosmic terms it is a blink, a thin boundary between fog and clarity. When we observe the CMB today, we see it cooled to just a few degrees above absolute zero. The expansion of space stretched those photons from visible and infrared energies down into microwaves, turning a searing early glow into a cold, uniform afterimage. The sky becomes a screen, and the CMB becomes the oldest light we can directly see. The CMB is nearly uniform, and that uniformity is a clue. It tells us the early universe was remarkably smooth, with tiny fluctuations at the level of tens of microkelvin. Those small variations later grew into galaxies and clusters, because gravity amplifies small differences over time. If you could translate the CMB into a visual map, it would look like a softly mottled sphere. Warm and cool patches would be sprinkled across it like faint freckles, each one a record of slightly different densities. Those differences are the seeds of everything structured, including the Milky Way and the atoms in our bodies. The third anchor is primordial element abundances. Hydrogen and helium dominate the cosmos, with traces of deuterium and lithium. These ratios are not arbitrary, and they are not set by stars alone. They match predictions from Big Bang nucleosynthesis, a calculation that depends on well-tested nuclear physics. In the first minutes, the universe was hot enough for nuclear reactions, but it cooled too fast to build heavy elements. Protons and neutrons combined into light nuclei, yet the window for fusion slammed shut as expansion diluted the fire. Stars would later forge carbon, oxygen, and iron in their cores. The early universe set the baseline, and stellar history wrote the rest. What makes this anchor powerful is its independence. The abundance of deuterium, for example, is exquisitely sensitive to the density of ordinary matter, so it acts like a cosmic scale. When observations of ancient gas clouds match the predicted ratios, they are not just confirming a story. They are confirming a temperature, a density, and a timeline. These three anchors agree on a single broad picture. The universe expanded from a hotter, denser state. It cooled as it grew, and it kept a record of that cooling in light and chemistry. Its early conditions can be inferred from multiple independent lines of evidence, which is why the rewind is more than metaphor. So far, the rewind feels straightforward. We move from galaxies to plasma to nuclear reactions to a younger cosmos, and each step backward tightens the constraints. The physics becomes simpler in a useful way, because the early universe is more uniform and less cluttered by complex structures. There is also a strange comfort in that simplicity. When the universe is hot and smooth, there are fewer moving parts, fewer special cases, fewer local accidents. The equations describe an average cosmos, and the average is easier to test. Then we push further toward the first fraction of a second. The temperatures become extreme, and the familiar categories of matter begin to blur. Energies approach those where our best-tested theories stop agreeing with each other, and the rewind starts to sound like a warning. General relativity describes space-time and gravity on large scales, treating gravity as geometry. Quantum physics describes matter and fields on small scales, where uncertainty and discrete interactions dominate. Near the beginning, we need both at once, in the same calculation, because the universe is small enough for quantum effects and massive enough for gravity. When we try to combine them, the math warns us. If we keep rewinding under classical general relativity, density and curvature blow up, and the equations produce infinities. Time seems to hit a boundary called a singularity, where the model declares its own breakdown. A singularity is not a place we can visit. It is a sign that the model has been pushed beyond its domain, like a map that stops at the edge of the paper. The equations are telling us they no longer know what before means, because their variables no longer behave. Historically, this was both a triumph and a discomfort. The same theory that explained Mercury's orbit and predicted black holes also implied an origin point where its own predictions became nonsensical. That tension is not a poetic flourish. It is a technical conflict, and it sits at the heart of modern cosmology. This is the central mystery of the documentary. We can trace the universe back to an early hot, dense state with confidence, because the evidence converges. We cannot trace it all the way to an intuitive beginning without changing the rules, because the tools we rely on stop working together. At this edge, nothing returns, but it changes shape. There is philosophical nothing, the absence of anything whatsoever, not even laws. There is physical nothing, which often means a vacuum state in quantum field theory, where no real particles are present. A vacuum is not empty in the everyday sense. It is the lowest energy state of fields, and it can still have structure, correlations, and measurable effects. Quantum fluctuations appear in calculations as temporary excitations, and even if the language of virtual particles is slippery, the underlying mathematics is not optional. In plain terms, quantum fields do not switch off just because the particle count is zero. They still have a ground state, and that ground state can carry energy and influence. The vacuum is closer to a calm ocean than a drained basin, still present, still capable of ripples. But even that nothing assumes a stage. It assumes space-time exists as a background where fields live and evolve, and it assumes time is available to define lowest energy. If spacetime itself is part of what began, then a vacuum may be too much like something, because it already grants us the arena. So we need a third notion: no classical spacetime. A regime where the smooth geometry of relativity is not a valid description, and where time may not be a fundamental parameter. In that regime, the universe may be better described by quantum relationships than by a continuous fabric. This is where the phrase "before the Big Bang" becomes dangerous. Before is a time word, and it assumes a timeline that extends beyond the event. If time is part of what emerges, then asking what happened before may be like asking what is north of the North Pole. That analogy can clarify, but it can also mislead. The North Pole sits inside a larger surface, and we can imagine stepping away in many directions. For the universe, we do not yet know what the larger structure would be, or whether there is one, so the metaphor must be handled carefully. Some cosmological models suggest a beginning in a strict sense, where time has a first meaningful moment. Others suggest a bounce from a previous phase, where contraction leads to expansion through new physics. Others suggest an eternal inflationary background spawning many regions, while some suggest time itself is emergent from deeper quantum relations. Each proposal tries to repair the broken reel without inventing miracles, yet each must eventually pay a debt to observation, because cosmology is not only storytelling. The question is always the same: what would this idea change in the sky we can measure? In this opening chapter, we do not choose a winner. We set the rules of the puzzle and we mark the boundary between confidence and conjecture. We separate what is measured from what is inferred and what is inferred from what is speculated, because those categories often blur in popular retellings. Measured, we have expansion, the CMB, and primordial abundances, each supported by instruments and surveys. Inferred, we have a hot early universe and a timeline back to fractions of a second, built from those measurements and established physics. Speculated, we have the origin of space-time and the meaning of nothing, where multiple frameworks compete. The tension is that our certainty grows as we rewind until it suddenly collapses. The closer we get to the putative beginning, the more the story depends on physics we have not yet tested in laboratories or observed directly in the cosmos. The frontier is not far away, it is embedded in the first instant. This is not a failure of curiosity, it is a map of the frontier drawn in the only honest way, by admitting where our methods still reach and where they do not. The boundary is precisely where new ideas must be judged, not by elegance, but by consequences that can reach our telescopes. Even the word "begin" needs care, because it hides multiple meanings. It can mean the earliest time our equations can describe without contradiction. It can mean the first moment that has physical meaning, if time itself is emergent. It can mean the start of our observable patch, not of all reality beyond it. The Big Bang in modern cosmology is not a single event we can point to like a spark. It is a framework that connects evidence to an evolving universe, and it works extraordinarily well. It is a successful rewind up to the point where the reel breaks and the missing frames become the subject. So we stand at the edge of the reel and look into the gap. Is the gap a true beginning, where time starts and questions stop? Or is it a veil, hiding a deeper description that makes before meaningful again? If the universe can be rewound to a boundary, what decides whether that boundary is a wall or a doorway? To answer, we will need to be precise about nothing, and ruthless about what counts as explanation. We will need to follow the evidence backward, then ask what kind of physics could replace the missing frames. We will also need to watch for a subtle trap, when a word feels clear, but the concept underneath is still undefined. Next, we begin the rewind in detail, using expansion, relic light, and primordial chemistry as our guide rails. We follow them toward the earliest moments we can still describe and the first moment we cannot. And when the reel finally tears, we will linger there, because that tear may be telling us what reality is made of. We ended at the edge of a rewind where before starts to wobble, and ordinary intuition loses its grip. Chapter 2 stays with what the universe actually left behind, because clues survive even when causes remain hidden. In science, the past is rarely a memory. It is a pattern preserved in light, in matter, and in the geometry between them. Cosmology works like forensics, except the crime scene is the sky, and the evidence is everywhere at once. We cannot rerun the beginning, but we can measure the debris field of light, motion, and composition. We can compare those measurements to physical laws tested in laboratories, and then ask which histories could have produced what we see. The case for a hot beginning is not one argument, but a convergence of independent witnesses that point to the same early conditions. First comes expansion, the simplest clue and the hardest to unsee once you know it is there. In the 1910s and 1920s, Vestus Slipher measured galaxy spectra and noticed that many were shifted toward the red, implying recession. A decade later, Georges Lemaitre connected that recession to general relativity, and Edwin Hubble tied it to distance using Cepheid variable stars as standard candles. The pattern was disarmingly clean. The farther the galaxy, the larger the redshift, as if space itself were pulling everything apart. In archival photographs, the early observatories look almost delicate. Glass plates, long exposures, handwritten logs. Yet the implication was enormous. The universe was not static, not eternal in the same unchanging form, and not content to sit still for human convenience. The Hubble-Lemaitre relation turned the sky into a graph, and that graph sloped upward. Each point on it was a galaxy, each galaxy a city of stars, and each one was telling the same story in a different accent. Redshift is often described as a Doppler effect, like a siren dropping in pitch as it passes you. That analogy is useful, but in cosmology the deeper point is stretching rather than motion through space. Space expands while light travels, and wavelengths lengthen with the metric that defines distances in an evolving universe. The photon is not tired, and it is not losing energy to friction. The ruler used to measure its wavelength is changing as the universe grows. Spectral lines make this measurable with almost unsettling precision, because quantum transitions act like identical clocks in every atom. Atoms and ions imprint specific absorption and emission features, each one set by energy levels that do not drift with cosmic time. Hydrogen's lines, calcium's lines, oxygen's lines, each is a barcode that can be recognized even across billions of light years. When those features slide toward longer wavelengths, the shift becomes a ruler. It tells us how much the universe expanded during the photon's journey, because the stretching factor is written directly into the spectrum. In visuals, you can imagine the spectrum as a piano keyboard of colors, with dark notches where atoms have removed light. As distance increases, the entire keyboard shifts, and the notches glide to the right in unison. That coherence is the point. Different elements move together, which is exactly what you expect from a global stretching of wavelengths. The redshift becomes a timestamp of expansion, a way to place each galaxy on the timeline. The Hubble-Lemaitre law turns recession into a map of history, because expansion is not merely a present-day fact. If distances are growing now, then distances were smaller earlier, and the same matter occupied less volume. Run the film backward and the average density rises, not because matter is created, but because the container shrinks. This is a geometric inference, and it is hard to evade without rewriting the meaning of distance itself. Temperature rises too, and this is where the logic becomes physical instead of purely geometric. Radiation cools as the universe expands, because photon wavelengths stretch and their energies drop. In plain terms, longer wavelength means lower energy per photon, and a bath of such photons looks colder. Reverse that stretching and the early cosmos becomes hotter, brighter and more energetic, with radiation packed into a smaller space. This is the first inference, and it is already a powerful one. Expansion implies a denser past, and a denser past implies a thermal past, because matter and radiation collide more often at higher densities. The Big Bang, in this evidence-based sense, is not an explosion in space with a center and an edge. It is the expansion of space from a hot, dense state, and every location becomes here when you describe it from within. Yet expansion alone is not enough, because clever alternatives can imitate a single clue. A hypothetical mechanism might mimic redshift without a hot origin, or it might mimic distance relations through some unknown dimming effect. So cosmology demands a second line of evidence, a relic that only a hot early universe would naturally produce. It asks for a signature that is difficult to counterfeit, because it depends on thermal physics rather than on one kinematic trend. That relic is the cosmic microwave background, the afterglow that fills the sky like a faint uniform fog. In 1965, Arno Penzias and Robert Wilson found a persistent microwave hiss that came from every direction. It did not track the Milky Way, it did not vanish with better shielding, and it did not care where they pointed their horn antenna. It looked like the sky itself was glowing, as if space were quietly warm. The discovery has an almost cinematic quality when you linger on the details, because it is science in its most human form. They cleaned bird droppings from the antenna, checked electronics, and chased every mundane explanation they could imagine. The noise remained, steady, isotropic, and stubbornly real, like a signal that refused to be dismissed as equipment trouble. At the same time, theorists had predicted that a hot early universe should leave behind a cooled remnant radiation field. The match between prediction and accident was not just lucky, it was clarifying, like a hidden layer of the universe suddenly made visible. The CMB is not light from stars, and it is not a diffuse glow from dust in our galaxy. It is thermal radiation from the early plasma, released when the universe became transparent. It is a snapshot of conditions when matter and radiation stopped constantly colliding, and that stop is a physical transition rather than a poetic phrase. Before transparency, photons were trapped in a dense sea of charged particles, scattering so often that they performed a slow random walk. To understand that, we rewind to the first few 100,000 years, when the universe was young but already governed by familiar microphysics. Early on, the universe was a hot plasma of electrons, protons, and helium nuclei, with photons vastly outnumbering baryons. Photons scattered off free electrons through Thomson scattering, a process with a well-known cross-section that makes the early cosmos effectively opaque. Light could not travel far without being deflected, so the universe behaved like the interior of a star, but on a cosmic scale. As expansion continued, the plasma cooled, and cooling here has a specific meaning. The average photon energy dropped as wavelengths stretched, and the rate of energetic collisions decreased. When temperatures fell to a few thousand Kelvin, electrons could bind to nuclei and stay bound, because the typical photons were no longer energetic enough to immediately knock them free. This transition is called recombination, though it is really the first stable combination in cosmic history, since there were no earlier atoms to recombine. Recombination changed the universe's visibility with a suddenness that is easy to underestimate. The moment most electrons became bound in neutral atoms, the number of free charged particles plummeted. With fewer free electrons, photons stopped scattering so often and began to stream freely across vast distances. This is photon decoupling, and it is not that photons choose to leave. It is that the fog thins until the mean free path becomes cosmological. The CMB is the light released at that moment, about 380,000 years after the hot beginning. In a visualization, you can picture a glowing, opaque sphere surrounding every observer, like a wall of light at the edge of visibility. We do not see earlier than that with electromagnetic radiation, because earlier photons were constantly redirected. The CMB is therefore a surface in time, not a physical shell in space, and it marks the limit of what light can directly show us. Those photons have been travelling ever since, and expansion has been stretching them the whole way. What began as a hot glow in the visible and infrared has been redshifted into microwaves. Today it has a near-perfect blackbody spectrum at 2.725 Kelvin, corresponding to a peak wavelength of a few millimeters. The number is small, but the meaning is large. It is the cooled remnant of a once blazing radiation bath. That blackbody detail matters because it is not a vague fit or a hand-waving resemblance. A blackbody spectrum has a specific shape, determined by Planck's law, and the CMB matches it with extraordinary precision across many frequencies. Any significant contamination from starlight, dust, or non-thermal processes would distort that curve. Instead, the spectrum is smooth in exactly the way thermal equilibrium predicts, as if the universe once behaved like a perfect oven. This is the thermal fingerprint of a universe that was once in near equilibrium, where matter and radiation exchanged energy rapidly. It also tells us something subtle about the early conditions. Equilibrium implies frequent interactions, and frequent interactions imply high density and high temperature. The CMB is not merely old light, it is old light that remembers being thermalized, and that memory is encoded in its spectrum. Uniformity is the next clue, and it is both reassuring and unsettling. The CMB temperature is almost the same in every direction, with variations at roughly 1 part in 100,000. In full sky maps, the dominant feature is smoothness, a soft gradient that mostly comes from our own motion relative to the CMB rest frame. Once that dipole is removed, the remaining pattern is a delicate speckling, like frost on glass. Those tiny variations are anisotropies, and they are not noise from our instruments. They repeat across experiments, across observing strategies, and across frequency bands designed to separate foreground emission. Satellites like COBE first detected them, then WMAP and Planck mapped them with increasing resolution and sensitivity. The consistency is the point. The universe is whispering the same fluctuations no matter how carefully we listen. Anisotropies matter because structure needs seeds, and the later universe is full of structure. Galaxies and clusters did not appear from a perfectly uniform fog because gravity has nothing to amplify if everything is exactly equal everywhere. Small overdensities grow as they attract more matter, and underdensities become voids as matter drains away. Over billions of years, this gravitational instability turns tiny contrasts into the cosmic web. The CMB shows those seeds before stars exist, before supernovae stir the gas, and before black holes reshape their neighborhoods. It shows the universe while it is still mostly simple physics: gravity, pressure, and radiation in a coupled plasma. That simplicity is precious because it limits the number of hidden variables. The early universe becomes a clean test of cosmological models, where the equations are tight and the data are global. The pattern is not random, and that is where the CMB becomes more than a photograph. In the early plasma, matter and radiation behaved like a coupled fluid, because photons and baryons were locked together by scattering. Gravity tried to compress denser regions, while radiation pressure pushed back, creating oscillations that are literally sound waves in the primordial medium. These are baryon acoustic oscillations in their earliest form, rippling through a universe that had not yet formed a single star. You can imagine these oscillations as expanding and contracting shells around initial overdensities. Where gravity deepens a well, the plasma falls in, heats, and pushes back, overshooting in a rhythmic cycle. The speed of these waves depends on the mixture of radiation and matter, and the damping depends on diffusion processes that blur small-scale features. Even here, the universe is doing laboratory physics, but at scales measured in hundreds of thousands of light-years. When decoupling happened, the oscillations froze into the CMB as a set of preferred angular scales. The plasma could no longer keep oscillating in the same way once photons streamed freely, so the pattern was locked in place. In the power spectrum, those frozen modes appear as acoustic peaks, a series of humps whose spacing and relative heights are diagnostic. It is a fingerprint that can be compared to theory with numerical precision. This is where cosmology becomes precision measurement rather than broad storytelling. The first peak tells us about spatial curvature, because curvature changes how a fixed physical scale projects onto the sky. If the universe was strongly curved, the same sound horizon would appear larger or smaller in angle. The fact that the peak lands where it does tells us the geometry is very close to flat, at least on observable scales. The relative peak heights tell us about baryon density and dark matter, because they change the inertia and gravitational driving of the oscillations. More baryons make compressions deeper and rarefactions different, altering the odd and even peaks in a characteristic way. Dark matter, which does not couple to photons, provides gravitational wells that shape the oscillations without adding pressure. The CMB therefore measures invisible ingredients by how they tug on visible plasma. The CMB does two jobs at once, and that dual role is part of its power. It confirms a hot, dense, early phase through its blackbody spectrum, which is hard to fake. It also constrains the parameters of the model through its anisotropies, turning the sky into a calibrated dataset. In effect, the universe provides its own boundary conditions, and we test our equations against them. Still, light is only one witness, and cosmology prefers a case with multiple independent testimonies. A third witness is chemistry, because the early universe also ran a brief nuclear experiment. It left behind a recipe that stars did not have time to rewrite completely, and that recipe is preserved in the most ancient, least processed environments we can find. Big Bang nucleosynthesis happened in the first minutes, when the universe was hot enough for nuclear reactions but cooling too fast to linger. At temperatures near 1 billion Kelvin, protons and neutrons collided and fused into light nuclei. The key point is timing, because expansion acts like a clock that shuts the reactions down. The universe cooled so quickly that fusion effectively ended before heavy elements could form, leaving a cosmos made mostly of the simplest nuclei. To see why heavy elements do not appear, you have to notice a bottleneck in nuclear physics. There are no stable nuclei with mass number 5 or 8, which makes it difficult to build heavier elements step by step in the early universe. Stars solved this later with long timescales and high densities, using processes like the triple alpha reaction to bridge gaps. The early universe does not have that luxury, because density and temperature are falling rapidly as space expands. Neutrons are unstable on long timescales, so the neutron-to-proton ratio mattered from the start. Weak interactions set that ratio early, keeping neutrons and protons in equilibrium through reactions involving neutrinos and electrons. As the universe expanded and cooled, those weak interactions froze out, meaning they became too slow to maintain equilibrium. Some neutrons decayed before they could be captured, and the remainder mostly ended up bound into helium-4, the most stable light nucleus. The result is a robust prediction, and robust here is a technical compliment. A hot early universe should produce about 3/4 hydrogen and about 1/4 helium by mass, with trace amounts of deuterium, helium-3, and lithium-7. The exact numbers depend mainly on the baryon density and known nuclear reaction rates, which can be measured in terrestrial experiments. That dependence is what makes nucleosynthesis a test rather than a story. Observations match the broad picture, and the match appears in places where stellar processing cannot easily fake it. Helium is abundant even where stars have not had much time to make it, such as in low metallicity gas and primitive galaxies. Deuterium is especially valuable because stars tend to destroy it when they burn hydrogen, so high deuterium points to primordial origin in relatively unprocessed gas. When we see deuterium at the expected level, it is like finding an untouched sample from the early universe. Deuterium also acts like a baryometer, because its predicted abundance is extremely sensitive to the density of ordinary matter during nucleosynthesis. If the baryon density were higher, deuterium would be burned more efficiently into helium, leaving less behind. If the density were lower, more deuterium would survive. When measurements in ancient gas clouds match the predicted deuterium fraction, they lock in the baryon density independently of the CMB, and the two methods agree remarkably well. Lithium is more complicated, and the complication is scientifically useful because it prevents complacency. The simplest predictions and some observations do not align perfectly, which may reflect stellar processing, atmospheric modelling uncertainties, or missing astrophysics in how lithium survives in old stars. In close-up visuals, an old, metal-poor star becomes a kind of archive, its spectrum a thin set of lines that must be interpreted with care. The mismatch is a reminder that cosmology is not a single victory lap. It is a network of checks, tensions, and refinements, where even small discrepancies can point to overlooked details. Taken together, expansion, the CMB, and primordial abundances form a tight triangle of evidence. Expansion tells us the universe was smaller and denser, and that density implies a hotter state. The CMB shows it was once hot, opaque, and then suddenly transparent, leaving behind a thermal afterglow. Nucleosynthesis shows it was hot enough for nuclear reactions, but only briefly, producing light elements in predictable proportions. This convergence is why the hot Big Bang is not a guess or a metaphor stretched too far. It is a reconstruction constrained by multiple independent datasets and by laboratory-tested physics, from atomic spectra to nuclear reaction rates. It is the earliest chapter we can read with high confidence, because the evidence is written into the sky in more than one language. Even when we argue about details, we argue within a framework anchored by these enduring traces. So far, the rewind feels straightforward. Each clue pulls us backward to simpler conditions, where fewer processes can hide the truth. The story becomes cleaner as we approach the beginning, and that cleanliness is itself a kind of constraint. When the universe is young, there are fewer stars, fewer galaxies, and fewer complicated environments to confuse the signal. But the clues also sharpen a new mystery, because they describe what happened after the hot phase began, not what caused that phase to start. They tell us the initial conditions were hot, dense, and expanding, and they tell us those conditions held with astonishing uniformity. They do not tell us why those conditions held across the whole observable sky. The evidence is strong, but it points to an edge where explanation becomes incomplete. The CMB's uniformity raises the horizon problem, a puzzle with a precise geometric meaning. Regions of the CMB on opposite sides of the sky were never in causal contact in the simplest hot Big Bang timeline. Light could not travel between them before decoupling, because the universe was only 380,000 years old and expanding rapidly. Yet their temperatures matched to extraordinary precision, as if they had once been in thermal contact. In a naive picture, they should not agree so well, and the naive picture is not silly. If distant regions could not exchange signals, they could not equilibrate, and their temperatures might differ significantly. On a space-time diagram, their path-like cones barely overlap, leaving almost no time for coordination. The universe looks like it coordinated its initial conditions across distances that should have been disconnected. That coordination is not impossible in principle, but it demands an explanation beyond the simplest extrapolation. The horizon problem is not a philosophical complaint dressed up as math. It is a quantitative mismatch between causal structure and observed uniformity, and it can be drawn cleanly with rulers and cones of light. It asks how the early universe arranged such similar conditions across regions that could not communicate under standard expansion. When the CMB looks smooth, it is not merely aesthetically pleasing, it is scientifically provocative. A second puzzle is flatness, and it emerges from how curvature behaves in general relativity. Spatial curvature evolves with expansion, and any small deviation from perfect flatness tends to grow in relative importance over time during standard matter and radiation eras. That means today's near-flat universe implies an even more exquisitely tuned flatness in the past. The earlier you set the clock, the more extreme the required tuning becomes. That near-flatness implies fine-tuning in the early universe if nothing else happened, and the numbers are uncomfortably sharp. Early curvature must have been set astonishingly close to zero, or else it would dominate later and spoil the observed geometry. In visual terms, the universe's trajectory seems to ride a narrow ridge. One small push, and the geometry would peel away. The model works, but it looks delicately balanced, like a pencil standing on its tip for billions of years. When a theory requires that kind of balance, physicists start looking for a mechanism that makes it natural. These puzzles do not overthrow the hot Big Bang, and they do not erase the evidence that supports it. Instead, they point to missing earlier physics that sets the initial conditions for the hot phase. They suggest that the hot Big Bang is not the whole beginning, but a later, well-tested era that follows some deeper prelude. The clues are consistent, yet they also hint that something happened to make them consistent. The CMB anisotropies deepen this point, because they do not merely exist, they have a particular statistical character. Their detailed spectrum fits a model with specific ingredients, including dark matter and dark energy, but it also encodes the initial perturbations. Those perturbations look nearly scale invariant and adiabatic, with phases consistent across modes. In practical terms, the fluctuations resemble a simple, coherent initial pattern rather than a chaotic patchwork. That pattern is a clue about the mechanism that generated the seeds. It looks less like a messy astrophysical process and more like a simple early universe process that imprinted correlations over vast scales. When the data show the same kind of fluctuation at many sizes, it raises a question. What produced a spectrum that is so close to a power law? The sky is not only telling us what happened, it is hinting at how the initial conditions were prepared. In other words, the evidence is doing two things at once, and that dual role shapes the mood of this chapter. It confirms the hot Big Bang as a successful description of early evolution, from minutes to hundreds of thousands of years. It also exposes the limits of that description, because it assumes initial smoothness, flatness, and the right spectrum of fluctuations. The model is powerful, but it is not self-originating. This is the boundary between reconstruction and origin, and the boundary feels like a change in lighting. Reconstruction uses known physics to infer earlier conditions from later traces, and it is strongest when the traces are clean. Origin asks why those conditions were selected, and whether before is even the right word when time itself is part of the system. The closer we get to the beginning, the more we discover that beginning is a word with hidden assumptions. We can push the hot Big Bang model earlier than recombination, and the mathematics remain steady for a long stretch. We can calculate back through nucleosynthesis, through neutrino decoupling, and into epochs where particle species change as temperatures cross mass thresholds. In those eras, the contents of the universe shift as heavier particles become rare and lighter ones dominate. The equations remain reliable as long as we stay below energies where unknown quantum gravity effects dominate. As we approach the first fraction of a second, the universe becomes a laboratory we cannot build, not even in principle. Temperatures rise to scales where the electroweak force behaves differently, and where speculative grand unification might occur. Particle reactions that are rare today become commonplace, and symmetries that are broken now may have been restored then. The further we go, the more we rely on extrapolations of known physics, and the more sensitive our conclusions become to assumptions. Even so, the direction is clear. Earlier means hotter, denser, and more symmetric in its fundamental interactions. Even before quantum gravity, there is a conceptual wall that the hot Big Bang does not cross. The hot Big Bang describes an expanding, cooling universe once it already exists as a spacetime with matter and radiation. It does not by itself explain why spacetime began expanding in that state, or why the initial conditions were so special. It is an evolution story, not an origin story, and the difference matters. This is where the documentary's central question returns with sharper edges than before. If the Big Bang is the earliest chapter we can read, what began that chapter? When science says nothing, does it mean an empty vacuum with laws, or the absence of space-time itself? And if the laws exist before, what does before even mean when time is part of the universe's geometry? The evidence does not answer that directly, but it narrows the options in a way that feels almost like pressure. Whatever the deeper story is, it must reproduce the expansion history, the CMB blackbody spectrum, the acoustic peaks, and the light element abundances. Any proposal for before has to pay that observational debt, because these clues are not negotiable. They are measurements, and measurements are stubborn. So the tone shifts from certainty to suspense, and the visuals can follow that shift. We have a model that fits the sky with remarkable precision, yet it carries questions it cannot settle from inside its own timeline. The clues point backward, then they stop, as if the trail reaches a cliff edge. At that edge, the universe is still speaking, but it is speaking in riddles. Then we push further, toward the first fraction of a second. The puzzles of horizon and flatness become signposts, suggesting a prelude to the hot Big Bang that reshaped the initial conditions. The next chapter follows that signpost into inflation, and into the uneasy phrase, before the Big Bang. Then we push further, toward the first fraction of a second where the hot Big Bang needs a prelude. The clues from Chapter 2 still stand, yet their smoothness demands a mechanism with reach. When we look at the CMB's near-uniform glow, we are really seeing a constraint on causality. How could regions that were never in contact end up sharing the same thermal story? Inflation is that proposed mechanism, an ultra-brief era of accelerated expansion, where distances grow exponentially rather than steadily. In a tiny interval, space can stretch by many orders of magnitude, turning microscopic regions into cosmic domains. The idea first took shape in the early 1980s, when cosmologists tried to reconcile particle physics instincts with a universe that looked suspiciously well-behaved. To picture it, imagine a grid drawn on space itself like faint graph paper across a dark stage. During inflation, the squares of that grid don't slide through space, they swell everywhere at once. Galaxies are not being flung through a pre-existing void. The ruler used to measure distance is what changes, and it changes in the same way across the entire inflating patch. This is not expansion into emptiness. It is the metric itself changing, so the meaning of distance evolves everywhere at once. If inflation happened, it happened everywhere in the region that later became our observable universe. The expansion is geometric, and in general relativity, geometry is not a backdrop. It is part of the physical system. Inflation is introduced because it makes the horizon problem less mysterious. In the standard hot timeline, opposite CMB patches were never in contact. Light and any other signal limited by the speed of light simply did not have time to cross the early universe before it became too large. Yet the CMB temperature varies only by tens of microkelvin across the sky, a smoothness that feels like a conspiracy. With inflation, those patches were once close enough to share a common temperature before being pulled far apart. The key move is causal, not cosmetic. Inflation makes today's observable universe originate from a much smaller connected patch. Uniformity becomes a memory of earlier contact, not an unexplained coincidence across disconnected regions. The visual implication is striking. We start with a tiny domain, small enough that particles and radiation can mix and equilibrate, like steam in a sealed chamber. Then the chamber's walls race outward faster than any signal can traverse the new distances. The heat remains uniform because it was uniform before the stretch, and the stretch preserves that uniformity while magnifying its scale. Inflation also addresses flatness through dynamics rather than tuning. Curvature scales differently than the energy driving accelerated expansion. In the Friedmann equations, the curvature term behaves like something that fades as the universe grows, while a nearly constant energy density refuses to dilute. Exponential growth pushes any initial curvature toward near zero, like stretching a curved surface until it looks locally flat. That explains why the first acoustic peak points to near-flat geometry. It reframes flatness as an attractor outcome, not a precarious initial balance. The universe looks geometrically simple because inflation makes complexity hard to keep. Even if the early geometry began slightly open or slightly closed, inflation would have ironed it toward a state that looks Euclidean over enormous distances. There is a subtlety here that makes the story more than metaphor. In a decelerating universe, small departures from flatness tend to grow in relative importance over time. That means a near-flat universe today would require extraordinary fine-tuning in the past. Inflation flips that logic by making near-flatness a natural late-time result of the inflationary phase. A third payoff is the monopole problem. Many high-energy theories predict heavy relics, including magnetic monopoles, produced in early-phase transitions. These are not whimsical additions. In grand unified ideas, the early universe can pass through symmetry-breaking transitions, and those transitions can trap topological defects, like knots in a field that cannot be untied locally. In a non-inflating hot history, those relics should be abundant, yet we do not see them. A single monopole would be unmistakable, a magnetic charge with no known conventional mimic. Their absence forces a choice. Either the theories are wrong, or the early universe had a way to dilute what it produced. Inflation dilutes relics by sheer volume growth. Any pre-existing monopoles are spread so thin that a Hubble volume today would likely contain none. The absence becomes compatible with early high-energy physics, without requiring monopoles never formed. In other words, inflation does not need to forbid relics. It merely makes them astronomically rare in the region we can observe. So far, inflation sounds like a patch that fixes multiple puzzles at once. The deeper reason it matters is that it can also generate the seeds of structure. It does not merely smooth the universe, it can write the initial pattern that later becomes galaxies. That is the point where inflation stops being a convenient repair and becomes a predictive engine. To see that, we have to take quantum uncertainty seriously as a physical source. In quantum field theory, fields fluctuate even in their lowest energy states. Those fluctuations are not optional noise. They are built into the commutation rules that define the theory, and they show up even when there are no particles in the classical sense. A useful way to hold the idea is to imagine every point in space as hosting a set of quantum oscillators. Even in the ground state, an oscillator cannot sit perfectly still. The uncertainty principle forces a residual jitter in field values and their conjugate momenta. In the lab, such fluctuations are usually microscopic and averaged away. During inflation, the universe turns the volume knob. During inflation, the relevant fields are stretched by expansion. Wavelengths that began far smaller than an atomic nucleus can be blown up to astronomical scales. A fluctuation that would normally remain microscopic becomes a classical-looking variation across huge regions. The expansion drags modes outward until their wavelengths exceed the Hubble radius, and at that point they effectively freeze as coherent patterns. This is the chapter's pivot. Inflation turns quantum randomness into macroscopic initial conditions. The earliest pattern we can measure may be a fossil of quantum jitters, amplified by the universe's fastest growth spurt. It is a startling inversion of intuition, because it suggests that the large-scale order of the cosmos began as small-scale indeterminacy. Visually, it is like watching ripples on a pond that is being stretched into a lake while the ripples grow with it. The ripples do not move faster than light, and nothing violates relativity. The surface itself is being extended, and the ripple pattern is carried along, enlarged until it spans distances that later become clusters of galaxies. The result is a spectrum of density perturbations. Small variations in energy density translate into small variations in gravitational potential. After inflation ends, those variations guide matter as it falls into wells and evacuates voids, building the cosmic web. Gravity, patient and relentless, converts tiny initial contrasts into the luminous architecture we see in surveys. The CMB anisotropies become the cleanest record of those primordial perturbations. They are measured as temperature differences, but they encode density and velocity variations in the plasma. The bright and dim patches correspond to compressions and rarefactions, sound waves in the early plasma, caught at the moment the universe became transparent. Those acoustic oscillations are not incidental decoration. They are the result of a tug-of-war between gravity, which tries to deepen over densities, and radiation pressure, which pushes back. The peaks in the CMB power spectrum are a kind of cosmic seismology. They tell us the initial conditions, the composition, and the geometry all at once. Inflation predicts those seeds should be nearly scale invariant. That means fluctuations have almost the same strength across a wide range of length scales. In practice, the power spectrum should be close to a simple power law, with a slight tilt. The tilt is not arbitrary. It reflects how slowly the inflaton's energy density changes during the inflationary roll. That prediction is not decorative. It is a quantitative target, and the CMB data land close to it. The near-scale invariant form was once a daring claim, because it links physics at unimaginable energies to patterns in a microwave sky map. Yet the measured spectral index sits just below exact scale invariance, a small deviation that is exactly what slow-roll inflation tends to produce. Inflation also predicts the perturbation should be close to Gaussian. Gaussian here means the fluctuations are well described by random phases with a simple two-point correlation. If you know the power spectrum, you know almost everything about the statistics. Non-Gaussian patterns can appear in some models, but the simplest versions keep them small. Observations so far are consistent with near-Gaussian initial conditions. That does not prove inflation, but it narrows the space of alternatives. It tells us the early universe was not seeded by a wildly nonlinear process. If the primordial pattern had been generated by violent, strongly coupled dynamics, we might expect distinctive higher-order correlations, and we do not see large ones. There is also a specific prediction about the perturbations type. Many inflation models produce mostly adiabatic perturbations, where different components fluctuate together. That means photons, baryons, and dark matter share the same fractional overdensity pattern. Like different instruments following the same score, that differs from isocurvature modes, where components fluctuate relative to each other, creating composition variations without total density changes. The CMB strongly favors adiabatic initial conditions. That aligns with the simplest inflationary picture, where one dominant field sets the clock. It also constrains multi-field scenarios that would leave different correlations. The early universe, at least as the CMB reveals it, behaves like a system with a single primary driver. To make inflation work as a physical phase, cosmologists introduce an inflaton field. The inflaton is a scalar field whose energy density is dominated by potential energy. When potential energy dominates, pressure becomes negative, and gravity becomes repulsive in the sense of accelerated expansion. This is a precise statement inside general relativity, where pressure gravitates alongside energy density. This is still general relativity. The acceleration comes from the stress energy content, not from a new gravitational law. In the Friedmann equations, a nearly constant energy density drives a near-constant Hubble rate, which produces exponential growth. The scale factor grows roughly like an exponential, and that rapid growth is what gives inflation its leverage. The inflaton is often described as rolling down a potential. If the potential is flat enough, the field rolls slowly. Slow roll keeps the energy density nearly constant, sustaining inflation long enough to solve the horizon and flatness problems. The slow here is not about human time. It is about how gently the potential slopes compared with the expansion rate. Slow roll also sets the perturbation spectrum. The shape of the potential influences the tilt and amplitude of fluctuations. In that sense, the CMB becomes a probe of a potential we cannot access in laboratories. We cannot build an accelerator to reach inflationary energies, but we can read the imprint those energies left on the sky. There is an additional layer of elegance in how the perturbations arise. Quantum fluctuations in the inflaton translate into fluctuations in the time inflation ends, from place to place. If one region exits inflation a fraction of a moment earlier, it has slightly less expansion, and that difference becomes a density contrast after reheating. The perturbations are, in a real sense, small wrinkles in the timing of the cosmic clock. Inflation must end, or it would erase the hot Big Bang entirely. Ending inflation requires a change in the inflaton dynamics, so the potential energy is converted into particles and radiation. This transition is called reheating, and it is the bridge to the familiar hot plasma. The universe goes from supercooled and vacuum-dominated to blazing and particle-filled, and that change is what makes the later thermal history possible. Reheating matters because it restores the conditions needed for nucleosynthesis and the later thermal history. It repopulates the universe with matter and radiation, setting the temperature that starts the hot Big Bang era. Without reheating, inflation would be an empty smoothing with no furnace afterward. The narrative would have a beautiful geometric prologue and no actual universe to inhabit it. The microphysics of reheating can be intricate. The inflaton may oscillate around the minimum of its potential, and those oscillations can decay into other fields. Sometimes the decay is slow and perturbative, like a dripping faucet of particle production. Sometimes it is explosive, a resonant transfer called preheating that can flood the universe with quanta in a short burst. The graceful exit problem is the technical version of that requirement. Inflation must stop everywhere in our region, and it must do so in a way that produces a hot, nearly uniform universe. Some early models struggled to end cleanly, or ended with unacceptable inhomogeneities. A graceful exit is not a luxury. It is the condition that makes inflation a prelude rather than a replacement. Modern models offer many exit mechanisms, but the variety is itself a warning. Inflation is a framework more than a single theory. Different potentials and couplings can fit the same broad data, so the question becomes which details are actually testable. When a framework is flexible, the burden shifts to observations that can discriminate among its internal possibilities. One of the most sought-after tests involves primordial gravitational waves. Inflation generically produces tensor fluctuations, ripples in spacetime itself. Their amplitude depends on the energy scale of inflation, so detecting them would measure the height of the inflaton potential. It would also be a rare direct window into quantum gravity's interface with cosmology, because these waves originate from quantized metric fluctuations. Those tensor modes would leave a specific imprint in CMB polarization. They can generate a Kerr-like pattern called B modes. The polarization map becomes a kind of forensic image, where E modes trace density-driven patterns and B modes hint at tensor ripples. Astrophysical foregrounds can also produce B modes, so the search is a careful subtraction, not a simple detection. Foregrounds are not a minor nuisance. Dust grains in our own galaxy align with magnetic fields and emit polarized light, creating patterns that can masquerade as primordial signals. Synchrotron radiation from charged particles spiraling in magnetic fields adds another polarized layer. The challenge is to separate a faint cosmological whisper from a loud local chorus, using multiple frequencies and meticulous modeling. A robust primordial B-mode signal would be a dramatic confirmation of inflation's quantum origin story. It would show that spacetime itself fluctuated and was stretched to cosmic scales. The absence of a detection so far pushes many models toward lower energy scales. It also encourages caution, because nature may be telling us that inflation, if real, operated below the most optimistic energy expectations. Even without B modes, inflation is tested through consistency. The scalar spectral tilt, the absence of large non-Gaussianity, and the adiabatic nature of perturbations all constrain the space of models. Each new dataset turns inflation from a story into a narrowing set of possibilities. The constraints do not merely confirm broad themes, they carve away entire families of potentials and couplings. Yet inflation also deepens the documentary's central question. It explains why the universe looks smooth, but it does not fully explain why inflation began. It shifts the origin problem from the hot Big Bang to the initial conditions of the inflating state. The moment we accept inflation as a prelude, we inherit a new prelude to inflation itself. What started inflation is not a single settled answer. Some proposals assume the inflaton began high on its potential in a small patch. Others rely on quantum tunneling into an inflating vacuum. Each proposal must still explain why that patch existed and why its conditions were suitable. The question is not just what field, but what prepared the field. There is also the question of whether inflation had a beginning at all. Many inflationary spacetimes are future eternal, because quantum fluctuations can keep some regions inflating while others exit. In that picture, inflation ends locally but continues globally, producing a multiverse of pocket universes. The term can sound speculative, yet it emerges from a straightforward competition between classical rolling and quantum kicks. Eternal inflation is not a poetic add-on. It is a consequence in some models of the same quantum fluctuations that seed structure. If fluctuations sometimes push the field uphill as fast as it rolls down, some regions keep inflating, and volume growth makes those regions dominate. The result is a fractal-like global picture, islands of reheated space embedded in a sea that keeps expanding. That leads to a new kind of nothing problem. If inflation is eternal to the future, it can populate reality with many regions, each with different low-energy outcomes. Our observable universe becomes one reheated bubble among many, and the question becomes why our bubble has its particular laws. Are the constants we measure a necessity, or a selection among possibilities? The past is even more delicate. Some theorems suggest that many inflating spacetimes cannot be extended infinitely into the past, at least under broad assumptions. That implies inflation may require some earlier boundary or new physics, even if it is future eternal. The mathematics does not tell us what the boundary is, only that the familiar inflationary description may not be the whole story. So inflation can be both an answer and a deferral. It answers why the universe is smooth and flat, and why perturbations look quantum and simple. It defers the deeper origin question to whatever sets up the inflaton, its potential, and the initial inflating patch. The more successfully inflation explains the observable universe, the more sharply it highlights what it does not explain. This is where the chapter preserves mystery rather than closing it. Inflation is powerful because it connects geometry, thermodynamics, and quantum theory in one mechanism. It is also unsettling because it makes the beginning feel less like a moment and more like a phase transition in an unknown larger story. We're used to beginnings that behave like events. Inflation invites beginnings that behave like regimes. So far, the rewind feels straightforward because the CMB and nucleosynthesis keep us anchored. Inflation pushes us into a prehistory where the evidence is indirect, encoded in statistics rather than images. We're still reading the sky, but now we're reading it as a fossil of dynamics we never directly observe. The data become less like a photograph and more like a fingerprint. If inflation happened, it sets the initial conditions for the hot Big Bang. It also turns the first measurable structure into a stretched quantum whisper. The earliest time we can talk about becomes tied to a field's evolution, not to a familiar clock. In that sense, time is not merely counted. It is defined by what changes. That reframes what begin might mean. The Big Bang becomes the start of the hot, particle-filled era, not necessarily the start of space-time. Inflation becomes a candidate for the missing frames, but it may itself require a prior chapter. The closer we get to the first instance, the more our language shifts from events to conditions. The origin question does not vanish. It moves deeper into the conditions that allow inflation to start, persist, and end. If reality can be eternal in some directions, then beginning becomes a concept we must define, not a point we can simply locate. Are we searching for a first moment, or for the rule that makes moments meaningful? Next, we follow that pressure toward the hardest edge. We ask what physics could precede inflation, or replace it, when space-time itself may be emergent. And we return to the word nothing, now sharpened by the fact that quantum fields never sit perfectly still. Then we push further toward the first fraction of a second, where the hot Big Bang needs a prelude. The clues from Chapter 2 still stand, yet their smoothness demands a mechanism with reach. That demand is not philosophical. It is written into the geometry of light cones, and into the limited time available for any early mixing. Inflation is that proposed mechanism, an era so brief that it can feel like a technical footnote, yet so violent that it reshapes the entire narrative. It is a period of accelerated expansion, where the scale factor grows faster and faster, and where distances increase exponentially rather than steadily. The word exponential matters because it multiplies, and multiplication outruns intuition. In a tiny interval, space can stretch by many orders of magnitude, turning microscopic regions into cosmic domains. A patch smaller than a proton can, in principle, become large enough to encompass everything we can see today. The numbers are extreme, but the logic is simple. If the expansion rate stays nearly constant while time advances, growth compounds. This is not expansion into emptiness. It is the metric itself changing, so the meaning of distance evolves everywhere at once. If inflation happened, it happened everywhere in the region that later became our observable universe. The expansion is not a wind blowing galaxies outward. It is the fabric of space-time rescaling, with no external outside required. The visual language of this matters for the viewer. We can show a space-time grid that starts tight and dense, then suddenly balloons its lines racing apart while the grid remains smooth. We can place a tiny causal patch in the center, then watch it inflate until it dwarfs the visible horizon. The image is not literal, but it conveys the core physical point. Inflation is introduced because it makes the horizon problem less mysterious. In the standard hot timeline, opposite CMB patches were never in contact. Their past-like cones do not overlap far enough back in time to allow thermal equilibrium across the whole sky. That means the uniformity we observe would be an unexplained initial condition, and cosmology tries to avoid unexplained initial conditions. With inflation, those patches were once close enough to share a common temperature before being pulled far apart. The key move is causal. Inflation makes today's observable universe originate from a much smaller connected patch. Uniformity becomes a memory of earlier contact, not an unexplained coincidence across disconnected regions. Think of the CMB as a sphere around us, a last scattering shell from when the universe first became transparent. Without inflation, the farthest points on that shell are too far apart to have coordinated their temperatures. With inflation, those same points were once neighbors, exchanging energy and information before the stretching made them strangers. Inflation also addresses flatness through dynamics rather than tuning. Curvature scales differently than the energy-driving accelerated expansion. If the energy density is nearly constant, while curvature dilutes rapidly as the universe grows, then curvature becomes negligible. Exponential growth pushes any initial curvature toward near zero, like stretching a curved surface until it looks locally flat. That explains why the first acoustic peak points to near-flat geometry. It reframes flatness as an attractor outcome, not a precarious initial balance. The universe looks geometrically simple because inflation makes complexity hard to keep. The geometry we infer is not a fragile accident. It is the expected residue of a phase that amplifies size while suppressing curvature. A third payoff is the monopole problem. Many high-energy theories predict heavy relics, including magnetic monopoles, produced in early phase transitions. These relics are not mere particles. They are stable configurations tied to the topology of fields, and they would survive cooling the way a knot survives the loosening of a rope. In a non-inflating hot history, those relics should be abundant, yet we do not see them. Their absence is a loud silence. It suggests either that the universe never went through the relevant transitions, or that something erased the relic density after it formed. Inflation dilutes relics by sheer volume growth. Any pre-existing monopoles are spread so thin that a Hubble volume today would likely contain none. The absence becomes compatible with early high-energy physics, without requiring monopoles never formed. Inflation does not need to deny the early universe's capacity to create exotica. It only needs to make that exotica practically unfindable within our horizon. So far, inflation sounds like a patch that fixes multiple puzzles at once. The deeper reason it matters is that it can also generate the seeds of structure. It does not merely smooth the universe. It can write the initial pattern that later becomes galaxies. This is where the mechanism earns its place, because it does more than repair. It predicts a specific kind of initial randomness. To see that, we have to take quantum uncertainty seriously as a physical source. In quantum field theory, fields fluctuate even in their lowest energy states. Those fluctuations are not optional noise. They are built into the commutation rules that define the theory. Even vacuum is a dynamic state, and it carries correlations that can be stretched and frozen. During inflation, the relevant fields are stretched by expansion. Wavelengths that began far smaller than an atomic nucleus can be blown up to astronomical scales. A fluctuation that would normally remain microscopic becomes a classical-looking variation across huge regions. The pattern becomes classical not because quantum mechanics stops, but because decoherence and horizon crossing make the phases inaccessible to local interference. This is the chapter's pivot. Inflation turns quantum randomness into macroscopic initial conditions. The earliest pattern we can measure may be a fossil of quantum jitters, amplified by the universe's fastest growth spurt. It is difficult to overstate how strange that is. The distribution of galaxies may trace back to uncertainty, written into the vacuum itself. The result is a spectrum of density perturbations. Small variations in energy density translate into small variations in gravitational potential. After inflation ends, those variations guide matter as it falls into wells and evacuates voids, building the cosmic web. In simulations, we can watch this happen. Filaments form, nodes brighten, and voids expand, all from tiny initial differences. The CMB anisotropies become the cleanest record of those primordial perturbations. They are measured as temperature differences, but they encode density and velocity variations in the plasma. The sky becomes a statistical map, and every multipole moment is a clue. The pattern is not random in the everyday sense. It is random with rules. Inflation predicts those seeds should be nearly scale invariant. That means fluctuations have almost the same strength across a wide range of length scales. In practice, the power spectrum should be close to a simple power law, with a slight tilt. The tilt is a slow roll fingerprint, a sign that the inflatance potential is not perfectly flat. That prediction is not decorative. It is a quantitative target, and the CMB data land close to it. The agreement is one reason inflation is taken seriously, even though its microphysics remains uncertain. A theory can be incomplete and still be powerful if it makes the right kinds of precise, falsifiable statements. Inflation also predicts the perturbations should be close to Gaussian. Gaussian here means the fluctuations are well described by random phases with a simple two-point correlation. Non-Gaussian patterns can appear in some models, but the simplest versions keep them small. The sky, in this view, is like a field of gently varying noise, with no sharp primordial spikes. Observations so far are consistent with near-Gaussian initial conditions. That does not prove inflation, but it narrows the space of alternatives. It tells us the early universe was not seeded by a wildly nonlinear process. It also tells us that whatever happened before the hot Big Bang did not leave obvious scars in higher-order correlations. There is also a specific prediction about the perturbations type. Many inflation models produce mostly adiabatic perturbations, where different components fluctuate together. That differs from isocurvature modes, where components fluctuate relative to each other. The distinction matters because it encodes whether the early universe had one dominant clock or several competing ones. The CMB strongly favors adiabatic initial conditions. That aligns with the simplest inflationary picture, where one dominant field sets the clock. It also constrains multi-field scenarios that would leave different correlations. The data do not forbid complexity, but they insist that complexity must hide behind a remarkably simple observable outcome. To make inflation work as a physical phase, cosmologists introduce an inflaton field. The inflaton is a scalar field whose energy density is dominated by potential energy. When potential energy dominates, pressure becomes negative and gravity becomes repulsive in the sense of accelerated expansion. This is a counterintuitive feature of relativity. Pressure contributes to gravity, and negative pressure can drive acceleration. This is still general relativity. The acceleration comes from the stress energy content, not from a new gravitational law. In the Friedmann equations, a nearly constant energy density drives a near-constant Hubble rate, which produces exponential growth. The universe behaves as though it is filled with an almost constant vacuum-like energy, and that energy dictates the expansion. The inflaton is often described as rolling down a potential. If the potential is flat enough, the field rolls slowly. Slow roll keeps the energy density nearly constant, sustaining inflation long enough to solve the horizon and flatness problems. It also prevents the inflaton from dumping its energy too quickly, which would end inflation before it has done its work. Slow roll also sets the perturbation spectrum. The shape of the potential influences the tilt and amplitude of fluctuations. In that sense, the CMB becomes a probe of a potential we cannot access in laboratories. The sky becomes a detector, and the detector's readout is a set of statistical parameters. Inflation must end, or it would erase the hot Big Bang entirely. Ending inflation requires a change in the inflaton dynamics, so the potential energy is converted into particles and radiation. This transition is called reheating, and it is the bridge to the familiar hot plasma. The universe must become hot again, not gradually, but decisively enough to begin the thermal story we can test. Reheating matters because it restores the conditions needed for nucleosynthesis and the later thermal history. It repopulates the universe with matter and radiation, setting the temperature that starts the hot Big Bang era. Without reheating, inflation would be an empty smoothing with no furnace afterward. The narrative would have a perfectly prepared stage and no actors. The graceful exit problem is the technical version of that requirement. Inflation must stop everywhere in our region, and it must do so in a way that produces a hot, nearly uniform universe. Some early models struggled to end cleanly, or ended with unacceptable inhomogeneities. A graceful exit is not just an aesthetic preference. It is the condition that keeps inflation compatible with the observed smoothness of the post-inflation plasma. Modern models offer many exit mechanisms, but the variety is itself a warning. Inflation is a framework more than a single theory. Different potentials and couplings can fit the same broad data, so the question becomes which details are actually testable. The more models survive, the more we need sharper observational discriminants. One of the most sought-after tests involves primordial gravitational waves. Inflation generically produces tensor fluctuations, ripples in spacetime itself. Their amplitude depends on the energy scale of inflation, so detecting them would measure the height of the inflaton potential. It would also connect the earliest universe to a phenomenon we understand well in another context: gravitational radiation. Those tensor modes would leave a specific imprint in CMB polarization. They can generate a curl-like pattern called B modes. Astrophysical foregrounds can also produce B modes, so the search is a careful subtraction, not a simple detection. The experiment is as much about understanding our galaxy as it is about reading the early universe. A robust primordial B-mode signal would be a dramatic confirmation of inflation's quantum origin story. It would show that spacetime itself fluctuated and was stretched to cosmic scales. The absence of a detection so far pushes many models toward lower energy scales. It also keeps the story open, because a non-detection can mean either that inflation was low scale, or that the tensor signal is simply beyond our current reach. Even without B-modes, inflation is tested through consistency. The scalar spectral tilt, the absence of large non-Gaussianity, and the adiabatic nature of perturbations all constrain the space of models. Each new dataset turns inflation from a story into a narrowing set of possibilities. The constraints are a kind of sieve, letting only certain inflationary shapes and couplings pass through. Yet inflation also deepens the documentary's central question. It explains why the universe looks smooth, but it does not fully explain why inflation began. It shifts the origin problem from the hot Big Bang to the initial conditions of the inflating state. The moment we accept inflation as a solution, we inherit a new why that sits behind it. What started inflation is not a single settled answer. Some proposals assume the inflaton began high on its potential in a small patch. Others rely on quantum tunneling into an inflating vacuum. Each proposal must still explain why that patch existed and why its conditions were suitable. The origin question becomes a question about the origin of a special state, not merely the origin of heat. There is also the question of whether inflation had a beginning at all. Many inflationary spacetimes are future eternal, because quantum fluctuations can keep some regions inflating while others exit. In that picture, inflation ends locally but continues globally, producing a multiverse of pocket universes. The word multiverse can sound like a leap, yet it can be the straightforward consequence of a stochastic process playing out on an inflating background. Eternal inflation is not a poetic add-on. It is a consequence in some models of the same quantum fluctuations that seed structure. If fluctuations sometimes push the field uphill as fast as it rolls down, some regions keep inflating, and volume growth makes those regions dominate. The global picture becomes one of ceaseless production, where reheated regions are constantly being born. That leads to a new kind of nothing problem. If inflation is eternal to the future, it can populate reality with many regions, each with different low-energy outcomes. Our observable universe becomes one reheated bubble among many, and the question becomes why our bubble has its particular laws. Are we seeing a unique necessity, or the outcome of a cosmic lottery weighted by volume and selection? The past is even more delicate. Some theorems suggest that many inflating spacetimes cannot be extended infinitely into the past, at least under broad assumptions. That implies inflation may require some earlier boundary or new physics, even if it is future eternal. The result is a tension that fits the tone of this documentary. Inflation is powerful, but it may not be ultimate. So inflation can be both an answer and a deferral. It answers why the universe is smooth and flat, and why perturbations look quantum and simple. It defers the deeper origin question to whatever sets up the inflaton, its potential, and the initial inflating patch. It is a bridge, and bridges imply shores on both sides. This is where the chapter preserves mystery rather than closing it. Inflation is powerful because it connects geometry, thermodynamics, and quantum theory in one mechanism. It is also unsettling because it makes the beginning feel less like a moment, and more like a phase transition in an unknown larger story. We are left with a beginning that behaves like a process, and a process that hints at an earlier condition. So far, the rewind feels straightforward because the CMB and nucleosynthesis keep us anchored. Inflation pushes us into a prehistory where the evidence is indirect, encoded in statistics rather than images. We're still reading the sky, but now we're reading it as a fossil of dynamics we never directly observe. The universe becomes a record of its own amplification. If inflation happened, it sets the initial conditions for the hot Big Bang. It also turns the first measurable structure into a stretched quantum whisper. The earliest time we can talk about becomes tied to a field's evolution, not to a familiar clock. The first whisper is not a sound. It is a correlation pattern imprinted across the sky. That reframes what begin might mean. The Big Bang becomes the start of the hot particle-filled era, not necessarily the start of space-time. Inflation becomes a candidate for the missing frames, but it may itself require a prior chapter. The closer we get to the origin, the more the origin behaves like a question we must formulate carefully. The origin question does not vanish. It moves deeper into the conditions that allow inflation to start, persist, and end. If reality can be eternal in some directions, then beginning becomes a concept we must define, not a point we can simply locate. What counts as the start if the mechanism that explains our beginning may be part of a larger ongoing process? Next, we follow that pressure toward the hardest edge. We ask what physics could precede inflation, or replace it, when space-time itself may be emergent. And we return to the word nothing, now sharpened by the fact that quantum fields never sit perfectly still. We have followed the rewind through inflation's hints, and the trail now narrows to a limit. The closer we get to the first instance, the more our equations stop behaving like guides, and the more they start acting like warning signs. On screen, the familiar timeline compresses until the labels crowd together, and the spacing between eras becomes almost comically tight. Galaxies blur into a pale mist, then into a uniform glow, and then into something our visual metaphors can barely hold. The universe does not simply get smaller in our imagination, it gets stranger because the rules we rely on begin to contradict each other. The camera keeps zooming, and the neat icons we use for matter and radiation lose their meaning. A smooth gradient becomes a restless shimmer, as if the picture itself is unsure what it should represent. We're watching a transition from a world of objects to a world of conditions, where even the idea of an object depends on the theory you trust. General relativity is our best theory of spacetime, as geometry and gravity as curvature. Quantum field theory is our best theory of matter, radiation, and the vacuum's restless structure, where even empty space is busy. Each works with astonishing accuracy in its own domain, and each has survived decades of experimental pressure. General relativity explains the precession of Mercury, the bending of starlight, gravitational waves, and the precise ticking differences of clocks in Earth's gravity. It also explains why GPS satellites must correct for both speed and gravity, or your phone's position would drift by kilometers each day. Quantum field theory explains the stability of atoms, the behavior of semiconductors, the magnetic moment of the electron, and the particle zoo produced in colliders. Quantum field theory is not just quantum mechanics with particles, but a framework where fields fill space and particles are excitations. Its predictions are statistical, yet they are so precise that tiny loop corrections can be measured in the lab. The trouble is not that either theory is sloppy, the trouble is that the early universe demands both at once. Near the beginning, the domains overlap, and the overlap is where the trouble starts. Energy densities rise, curvature tightens, and quantum fluctuations refuse to stay small. The universe becomes a laboratory that forces gravity to be quantum, and forces quantum fields to live on a space-time that will not sit still. In popular language, the Big Bang begins with a singularity, a point of infinite density and temperature. In physics, a singularity is not primarily a place, and it is not automatically an actual infinity. A singularity is often a signal that the mathematical description has reached the edge of its validity, like a map that ends not because the Earth ends, but because the cartographer ran out of reliable measurements. That distinction matters, because physics is full of ends of the map that later became gateways. When Newton's gravity failed near Mercury, it did not mean planets were impossible. It meant the rules were incomplete. Singularities can play the same role, where the breakdown is not a disaster, but a clue about what the deeper description must contain. The cleanest definition used by relativists is geodesic incompleteness. A geodesic is the path a free-falling object follows when no forces act except gravity, and it is also the path a light ray follows through curved spacetime. If you can extend every geodesic smoothly to arbitrary values of its parameter, spacetime is complete. If some geodesics end after a finite amount of proper time, the spacetime is incomplete. On screen, imagine a bundle of lines moving through a curved grid, like threads sliding across a stretched fabric. In ordinary regions, the threads can be traced indefinitely, even if they bend and converge. Near a singular boundary, some threads simply stop. There is no next square of grid to enter, no continuation the geometry will allow. Proper time is the time measured by a clock moving along that path, and it is the closest thing relativity has to an objective ticking. It is what a wristwatch would record if you could carry it along a freefall trajectory without disturbance. When proper time ends after a finite interval, the theory is telling us that an observer's history cannot be continued within that spacetime. It is not merely that something dramatic happens, it is that the mathematical structure refuses to supply a next moment. The equations still exist on paper, yet the spacetime they describe has run out of definable extension for certain observers. That ending is not a crash into a physical wall you can stand on. It is the failure of the spacetime manifold to provide a continuation of the path, even though the equations insist the path should exist. The theory says there is no further there along that trajectory. That is a different claim than saying some measured quantity literally becomes infinite. In practice, incompleteness often comes with diverging curvature, density, or tidal forces. Curvature is not a vague word here. It is encoded in tensors that measure how nearby geodesics converge or shear apart. The Riemann curvature tensor, and contractions like the Ricci scalar, turn the intuitive idea of bending into a precise bookkeeping of how geometry deviates from flatness. Tidal forces are the physical face of that curvature, the stretching and squeezing that gravity produces when it varies across a body. They are why the moon raises tides on Earth, and why a black hole can spaghettify matter near its horizon. In cosmology, tidal terms can also describe how neighbouring world lines in the expanding fluid accelerate relative to each other. If you could ride a free-falling elevator towards such an endpoint, you would not necessarily see a sign that says infinite. You would see the predictions become unstable, as if the theory's internal bookkeeping is tearing. The key point is logical, not sensational. The equations stop giving answers that can be interpreted as a smooth physical history. When this happens, physicists treat it as a warning label. It is the same instinct that treats a division by zero as a message, not as a physical event. The singularity is not a trophy for having reached the beginning. It is a marker that we have pushed a classical description into a regime where it cannot be trusted. Infinite has a specific role in physics, and it is rarely an endpoint. Infinities often appear when a model is pushed beyond its regime, or when important degrees of freedom are missing. They are frequently the shadow cast by an approximation that has been stretched too far. Classical electrodynamics once predicted infinite self-energy for point charges, because the electric field grows without limit as you approach a mathematical point. That infinity was not cured by better algebra. It was cured by a deeper framework where quantum mechanics and later quantum field theory changed what point-like means in practice. In that older picture, the electron was treated as a literal geometric point with a field that diverged at zero distance. In the quantum picture, you cannot pin down a particle's position without paying an energy cost, and that cost reshapes the story. The divergence becomes a sign that the classical picture is asking a question nature does not allow you to ask so sharply. In fluid dynamics, idealized shocks can create divergences that disappear when microscopic physics is included. Viscosity, molecular collisions, and finite mean-free paths soften what the perfect equations make sharp. The lesson is not that the equations were useless. The lesson is that they were incomplete at small scales. Cosmological singularities may be similar. The Big Bang singularity in classical general relativity may not be a real point in nature. It may be the place where classical spacetime stops being a good approximation, and where a new description replaces the old one. To see why, we need the Planck scales, where gravity and quantum effects become equally strong. The Planck length is about 10 to the 35 meters, far smaller than any particle scale we can probe directly. The Planck time is about 10 hours 43 seconds, the time light takes to cross a Planck length. The Planck energy is enormous, around 10 to 19 GeV, far beyond any accelerator. A visual ladder helps here. We drop from human scales to mountains to cells to atoms to nuclei to quarks, and then the rungs keep going until the labels become almost abstract. The ladder does not just shrink, it begins to feel like it is leaving the world of measurement behind. At the bottom, the Planck length is not merely small, it is so small that our usual idea of distance may no longer apply. These numbers are not arbitrary. They come from combining the constants that define relativity, quantum mechanics, and gravity. Put Planck's constant, the speed of light, and Newton's constant into one-dimensional recipe, and these scales appear. That is nature telling us where our separate theories are forced to meet. At the Planck energy, the gravitational interaction between particles becomes comparable to the other fundamental interactions. At the Planck density, packing energy into a region tends to curve spacetime so strongly that the region threatens to form horizons. Yet quantum mechanics insists that energy cannot be localized without uncertainty, and that uncertainty itself carries energy. This is where the intuition becomes slippery. If you try to confine energy to a smaller region, the uncertainty principle pushes momenta higher, and higher momenta increase energy. If you push far enough, the energy you use to localize the system contributes significant gravity, and gravity reshapes the region you are trying to define. Before the Planck time, our usual extrapolation becomes suspect. Energy densities approach the Planck density, and quantum fluctuations of geometry itself may become large. The smooth spacetime used by general relativity may not exist as a classical object, the way a smooth ocean surface fails to exist when you zoom down to individual molecules. On screen, the calm grid of spacetime can begin to flicker, as if the lines are no longer drawn in ink but in probability. The metric, which once looked like a stable coordinate mesh, becomes a trembling pattern of alternatives. What we call distance may become a statistical outcome, not a fixed property you can read off a ruler. The vacuum assumed by quantum field theory may not sit on a stable background. In ordinary quantum field theory, the vacuum is defined relative to a notion of time and a notion of particles. In curved, rapidly changing spacetime, those notions become observer-dependent, and the vacuum becomes a more delicate concept. Even in less extreme settings, curved spacetime already complicates the idea of a particle. What one observer calls empty, another can describe as filled with quanta, because the splitting between positive and negative frequency depends on the geometry. Near the beginning, where geometry itself is changing violently, that ambiguity is not a subtlety. It is the main event. General relativity treats spacetime as a differentiable manifold with a metric defined at every point. The metric is not just a ruler. It is the object that tells clocks how to tick, tells light how to travel, and tells matter how to fall. Quantum field theory typically assumes a fixed spacetime background, then quantizes fields that live on it. In everyday conditions, this division works because spacetime curvature is gentle and quantum gravity effects are tiny. Near the beginning, the background is the problem, because the background is what should be fluctuating. If energy is concentrated enough, the metric becomes highly curved, and the notion of a fixed stage collapses. If quantum fluctuations are strong enough, the metric cannot be treated as a single classical geometry. We need a framework where geometry can be in quantum superposition, or where space-time emerges from deeper variables. That framework is what people mean by quantum gravity. It is not one equation we have misplaced. It is a demand that two successful languages be translated into a single grammar. The difficulty is not just technical, and it is not just missing cleverness. The two theories encode reality in different languages, and they disagree about what is fundamental. General relativity is geometric and background independent, where the metric is dynamical and spacetime is part of the system. Quantum field theory is probabilistic and usually background dependent, where time is an external parameter that orders evolution. In quantum mechanics, time is the stage direction. In general relativity, time is part of the cast. Historically, this clash has been visible for almost a century. Einstein's theory arrived in 1915, and quantum mechanics matured in the 1920s, yet their union has resisted every straightforward attempt. The early successes of quantum electrodynamics and the Standard Model sharpened the contrast, because they showed how well the quantum approach works when the stage is fixed. When you try to quantize gravity naively, you run into non-renormalizable infinities that resist the standard cures. Renormalization is the method that lets quantum field theory absorb infinities into a small set of measurable parameters, leaving finite predictions. For gravity treated as a standard quantum field, the required counterterms multiply without end. In plain language, the theory demands an ever-growing list of new parameters to patch its own short-distance behavior. Each new parameter would need to be measured, and the predictive power drains away. That is why physicists say the naive approach is not a complete fundamental theory, even if it can still be useful at low energies. Those infinities are not proof that quantization is impossible. They are evidence that the straightforward approach is incomplete because it assumes the wrong degrees of freedom at high energy. Effective field theory can still describe low-energy quantum corrections to gravity, and it does so in a controlled way. But it does not provide a full ultraviolet completion. The beginning of the universe is an ultraviolet question. It is the question of what happens when we push to the shortest distances and highest energies, where the details of the fundamental description matter. This is why the singularity is not just a dramatic word. It is a marker that our current theoretical bridge ends, and it ends for a reason that can be stated precisely. On one side is classical space-time and well-tested cosmic evolution. On the other side is a regime where our basic assumptions about space, time, and measurement may fail. Classical general relativity does not merely suggest singularities in special solutions. It predicts them under broad conditions, through the singularity theorems. The theorems associated with Hawking and Penrose show that, given certain assumptions, space-time must be past incomplete in an expanding universe like ours. Historically, this was a turning point. In the early decades after Einstein, singularities were sometimes treated as artifacts of symmetry, or as curiosities of idealized solutions. The theorems changed the mood because they showed that singular behavior is not rare. Under reasonable conditions, it is generic. On screen, archival portraits can fade into diagrams of light cones, where the future opens like a funnel and the past narrows like a throat. The geometry itself becomes a character, guiding world lines into convergence. The message is unsettlingly simple. If gravity focuses paths strongly enough, the past can run out. The assumptions are important because they tell us where the escape routes might be. One assumption is that general relativity holds as a classical theory at arbitrarily high curvature. Another is that certain energy conditions hold, meaning matter behaves in ways that keep gravity attractive and keep geodesics focusing. Another is that causality behaves normally, without exotic loops or breakdowns. The theorems also rely on global features of spacetime, such as the existence of trapped surfaces, where even light rays are forced to converge. These are not exotic mathematical decorations. They are the geometric mechanisms that make collapse and past boundaries hard to avoid. A trapped surface is a particularly vivid idea. In ordinary space, light emitted outward can spread, and the area of a light front can grow. In a trapped region, even outgoing light is dragged into convergence, as if geometry itself is closing the exits. If those assumptions hold, then an expanding universe with sufficient focusing of geodesics cannot be extended indefinitely into the past. The result is not necessarily an infinite density point you can locate on a diagram. The result is that classical spacetime has a boundary in the past, a place where the classical description cannot be continued. The theorem is about the limits of extension, not about the material content at the endpoint. It does not tell us what replaces the boundary. It tells us that, within the classical rules, the boundary is unavoidable. Inflation does not automatically evade this conclusion. Some inflationary spacetimes are also past incomplete under broad conditions, even if they are future eternal. That means inflation can smooth and stretch, yet still require an earlier boundary or new physics. The prelude may still have a first unreadable frame. We can imagine the camera rewinding through the inflationary expansion, only to find that the film itself becomes grainy, then torn as we approach the earlier segment. The closer we get, the more the very notion of frame begins to fail. So the question becomes which assumption fails near the beginning. Quantum effects can violate classical energy conditions, and we already know vacuum energy behaves strangely. In quantum theory, energy density can be negative relative to a chosen reference, although usually only in constrained settings and for limited durations. Those negative contributions can alter the focusing of geodesics, which is central to the singularity theorems. Even the concept of matter behaves normally becomes slippery when the vacuum itself gravitates. At Planck scales, the very concept of a classical geodesic may not apply, because the path assumes a smooth geometry to travel through. Another assumption that can fail is the classical notion of space-time continuity. If space-time has a discrete or foamy structure at the smaller scales, the manifold picture breaks. A geodesic might not be definable the way it is in smooth geometry, because there may be no smooth curve to define. Incompleteness might then reflect the wrong mathematical arena, not a physical edge. The endpoint could be like the edge of a grid used to approximate a curve, where the curve continues but the grid cannot represent it. The warning sign would be telling us to change coordinates in a deeper sense, to change the very objects we treat as real. Different quantum gravity approaches propose different replacements for the classical picture. In loop quantum gravity, geometric quantities like area and volume become quantized, and the spectrum of these operators has a smallest non-zero value. That discreteness can act like a pressure against collapse, and singularities may be replaced by bounces. The image here is not a rubber sheet that can be pinched to a point. It is a fabric woven from minimal threads, where you cannot shrink an area below a smallest unit. If collapse tries to force geometry past that unit, the theory can redirect the evolution, turning end into turnaround. In string theory, extended objects and dualities can soften short-distance behavior, and extra dimensions can reshape what small means. A string cannot probe distances shorter than its own characteristic length without exciting new modes, which changes the ultraviolet story. The mathematics suggests that what looks like a singular point in one description can become smooth in another. Here the visual metaphor shifts. Instead of points colliding, we see vibrating filaments, whose internal motion stores the energy we try to pack into a point. Short distances become less like a destination and more like a transformation, where new degrees of freedom appear before the classical notion of smaller can complete. In causal set ideas, space-time is built from discrete causal relations, and continuity is emergent. The fundamental structure is not a fabric with points. It is a partial order of events, where before and after are primitive, and distance arises statistically from the density of relations. These are not settled answers, and they do not yet form a single tested theory. They are attempts to respect what we already know, while repairing what breaks. The common theme is that the singularity is not treated as a physical object. It is treated as a sign that the classical variables are the wrong ones. Even if quantum gravity resolves the singularity, it may not give us a simple before in the everyday sense. In cosmology, time is not a universal external parameter. Cosmic time is defined by the expansion history and by the motion of matter that defines a comoving frame, where the universe looks homogeneous on large scales. Near the beginning, the conditions that make a clean cosmic clock may not exist. If the universe is dominated by quantum fluctuations of geometry, there may be no stable notion of co-moving observers to carry synchronized clocks. The very idea of a global time coordinate can become an approximation that only emerges later. In general relativity, time is part of the geometry, and different observers slice space-time differently. In quantum theory, time is usually the parameter that tells a state how to evolve, while observables become operators. When the geometry is quantum, the role of time becomes ambiguous. This is the problem of time in quantum gravity. It is not a philosophical puzzle added for drama. It is a technical and conceptual obstacle that appears when you try to write a quantum equation for the universe as a whole. If the universe is described by a quantum state of geometry and matter, there may be no single external time variable. Evolution might be encoded as correlations between degrees of freedom, where one subsystem acts as a clock for another. Time may be emergent, not fundamental, and emergence here means derivable in a limit, not imagined into existence. That idea forces a quiet but profound question. If time is a relationship, what happens when the relationships are too noisy to define? What does change mean when the system has no stable parameter that plays the role of a ticking background? If time emerges, then before the Big Bang may be a category error. The question uses a grammar that assumes a timeline already exists. It assumes that the universe sits inside time, rather than time being one of the universe's properties. This is not a claim that nothing happened. It is a claim that the word before assumes a temporal ordering that may not exist at the deepest level. Asking what happened before time may be like asking what is north of the North Pole. The question points to a boundary in the coordinate system, not necessarily a boundary in reality. Still, the analogy has limits, and the universe is not a globe we can step around. The deeper point is that our most basic words may be tied to emergent conditions. Still, cosmology cannot stop at wordplay, because the universe left evidence that demands a physical account. If time emerges, we should ask what conditions make it emerge, and what observables carry traces of the transition. What would it mean in data to see the birth of a classical clock? A quantum gravity era might leave signatures in primordial gravitational waves, in non-trivial correlations, or in departures from standard inflationary predictions. It might alter the statistics of fluctuations, change the spectrum's tilt, or introduce subtle features that survive the later expansion. The challenge is that many signatures are subtle, and many models are flexible. On screen, the cosmic microwave background becomes more than a pretty map. It becomes a fossil surface, a record of tiny temperature differences that encode quantum fluctuations stretched to astronomical size. The question is whether that fossil also carries a faint imprint of the regime where space-time itself was fluctuating. The map's mottled colours are not noise. They are a snapshot of a plasma cooling into transparency, where photons finally decoupled and began free streaming across the cosmos. Each hot and cold spot is a density variation that later helped seed galaxies, and each variation began as a quantum uncertainty. We can frame the Planck era as the last place where the rewind is anchored by tested physics. After that, we're extrapolating beyond direct experimental support, guided by consistency rather than confirmation. The Planck time is not the moment the universe began, and it is not a proven boundary. It is the moment our current tools stop being reliable. It is the line on the graph where error bars are not just large, they are undefined, because the framework used to compute them is in doubt. In that sense, Planck time is less a date in cosmic history than a signpost on the road of inference. That limit changes how we interpret the Big Bang itself. The hot Big Bang is a well-tested description of an early hot, dense, expanding phase. It includes a thermal plasma, nuclear reactions that forge light elements, and a cooling history that leads to atoms and then to the CMB. The singularity is not part of that tested description. The singularity is what appears when we insist on extending classical equations past their jurisdiction. In other words, the hot Big Bang is a chapter we have evidence for. The singularity is a punctuation mark inserted by a model that has been overextended. So we separate two ideas that are often fused. One is the early hot phase, which is supported by the CMB, nucleosynthesis, and expansion. The other is the claim that the universe began at a literal point of infinite density. The first is evidence-based reconstruction. The second is a mathematical extrapolation that likely marks missing physics. Holding them apart is not evasive. It is how science stays honest about what is measured and what is inferred. This is where the documentary's central question tightens. If the earliest reliable chapter is not the first page, then nothing becomes harder to define. If classical spacetime fails, then nothing cannot mean empty space with no matter, because space itself is part of what is missing. The candidate nothings become more abstract and more physical. They are not poetic voids. They are specific states described by equations with constraints, symmetries, and allowable fluctuations. One candidate is the quantum vacuum, which is not nothing in the everyday sense. In quantum field theory, the vacuum is the lowest energy state, filled with fluctuations and structured by fields and symmetries. It can have energy, it can polarize, and it can produce particles in curved spacetime or in strong fields. Even when no particles are present, fields still have zero-point motion, and that motion has measurable consequences. The Casimir effect, for example, shows that boundaries can change the vacuum's energy density in ways that produce a force. Yet the vacuum still assumes a spacetime arena, with a metric that defines distance and a time coordinate that defines energy. So the vacuum is not nothing, but it is a kind of minimal something, defined by the rules of the theory. It is also not unique in all circumstances because different observers can disagree about what counts as empty. That observer dependence is a hint that emptiness is not a simple substance, but a relationship between fields and geometry. Another candidate is a quantum gravitational ground state, where spacetime is not classical and may not be defined at all. In that picture, the universe could arise as a transition from a non-classical regime to a classical expanding geometry. The beginning would be a change of phase, not a creation event in time. The word nothing would refer to the absence of classical geometry, not the absence of physical law. That distinction matters, because laws can exist as relationships among variables even when the familiar stage is missing. The unsettling possibility is that no space and no time does not mean no structure. A third candidate is that there is a prior history, but it is not accessible in the usual way. A bounce could replace the singularity, turning contraction into expansion. A pre-Big Bang phase could exist in a different branch of a larger theory. A multiverse background could spawn regions like ours through tunneling or reheating events. These ideas differ in their mechanisms, but they share a theme. The classical beginning may be a transition, not an absolute origin. Each option has a different relationship to time and causality. A bounce preserves a notion of earlier and later, but changes the high-density behavior. A tunneling origin may treat time as emerging after the transition, with a Euclidean or timeless description underneath. A multiverse picture may have time globally, but not a single beginning. It replaces one origin question with a deeper one, and it forces us to ask what counts as an explanation when the background is larger than our observable domain. The hard part is that many of these ideas live behind an observational horizon. If the Planck error scrambles information, then details of before may be erased, leaving only coarse features. Inflation itself can wash away traces of earlier conditions, making our observable patch insensitive to what came before. The universe may be built to hide its own origin, not by intention but by dynamics, by the way rapid expansion and thermalization can erase memory, the way a stirred fluid forgets the exact pattern of its initial swirl. Even in the best case, we may only recover statistical fingerprints, not a frame-by-frame recording of the earliest transition. Yet we can still learn something from the shape of the limit. The singularity theorems tell us that classical expansion wants a boundary in the past. The Planck scales tell us where quantum gravity must matter. The problem of time tells us that before may not be fundamental. Together, they tell us why the origin question is difficult in a precise way. The mystery is not a blank space. It is a sharply defined frontier, with signposts that point to what must change. This chapter's conclusion is not that science has failed. It is that science has located the edge of its current map, and it has described that edge with unusual clarity. The edge is not ignorance in general, it is a specific mismatch between two successful frameworks, revealed by the universe's earliest conditions. So far, the rewind has been a story of clues becoming cleaner as we go back. Now the rewind becomes a story of language and equations losing their footing, even as the evidence remains stubbornly real. When we say, the beginning, we may be naming the boundary of a model, not the birth of reality. The next step is to ask what nothing could mean when quantum theory is the only language left. If classical time fails, we must ask whether the universe could arise from a quantum vacuum or from a deeper pre-geometric state. The question shifts from what happened before to what it means for something to happen at all. Then we turn from broken equations to candidate origins that treat nothing as a quantum state. We follow the idea that emptiness can still have structure, and that structure may be enough to start a universe. We have followed the rewind to the edge where equations break and language starts slipping in our mouths. The closer we get to the beginning, the more the story depends on what we mean by a single word. When we say the universe came from nothing, we must ask what nothing means, because the word sounds simple while hiding several claims that do not agree. On screen, the rewind is clean and cinematic. Galaxies collapse into a bright haze, the haze compresses into a hot fog, and the fog becomes a single point. Yet the real boundary is not a dot in space, because space itself is part of the question. The moment we treat nothing as a place, we have already added structure, and the moment we treat nothing as a time, we have already assumed a clock. So the first task is not to solve the origin, but to stop smuggling in a stage that quietly does explanatory work. In philosophy, nothing means non-being, the absence of anything at all, without remainder. No objects exist, no properties exist, and no rules exist to describe them, not even in principle. This is not empty space, because space would already be something with geometry and extension, and geometry already implies relations. It is not a vacuum, because a vacuum is a state within a theory, and a theory is already a kind of something. Philosophical nothing is not a thin gas, not darkness, not a silent room, and not a blank page waiting to be written on. It is the denial of all categories that could even host a description, so even absence becomes a dangerous word. That definition has an austere clarity, and it is also brutally demanding. If there are no properties, then there is no state to label, and no before in which it could wait. If there are no rules, then there is no probability to assign, and no logic of change to apply. In that sense, philosophical nothing is not merely empty, it is unnameable without contradiction, because naming it treats it as an object with at least one attribute. In quantum physics, nothing often means the quantum vacuum, the lowest energy state of fields. Fields still exist, and their ground state still has structure, even when no particles are present. The vacuum is defined by equations, symmetries, and commutation rules that never turn off, even at absolute zero. Calling that nothing can be useful shorthand, but it can also mislead, because it makes the vacuum sound like a blank container. In reality, it is closer to a tightly constrained baseline, like a musical instrument at rest that still has allowed resonances. Historically, this shift in meaning did not happen in a single leap, and it carries the fingerprints of earlier debates. Classical physics had a comfortable picture of emptiness as an absence of matter, and the old luminiferous ether was rejected after experiments in relativity. Yet quantum theory quietly rebuilt a new kind of medium, not as a substance you could scoop, but as fields you cannot remove. In modern particle physics, the vacuum is not what remains when you take things away. It is the reference state of the fields that define what things can be, including what counts as a particle and how it can interact. A third meaning is more radical, and it matters for the Big Bang boundary. Nothing can mean the absence of classical spacetime itself, not merely the absence of particles within spacetime. If there is no classical geometry, there is no place for fields to live in the usual way, and there may be no global time to define energy. Then even the word vacuum becomes ambiguous, because vacuum assumes time, energy, and a background. It assumes that lowest energy is a meaningful phrase, and that assumption can fail near the limits where spacetime is expected to be quantum. These meanings are often blended in popular accounts, and the blend creates false drama. A quantum vacuum is not philosophical nothing, and a pre-geometric state is not empty space. When we conflate them, we smuggle in assumptions while pretending we removed everything, and the story gains paradox at the price of precision. The central question becomes sharper when we separate the definitions, and we watch how each one behaves under pressure. The aim is not pedantry, because the details change what counts as an explanation and what counts as a leftover premise. The quantum vacuum begins with the uncertainty principle, not with particles popping from literal emptiness. In quantum theory, conjugate quantities cannot both be pinned down exactly, even in principle, because their operators do not commute. For fields, that means field values and their momenta cannot both be perfectly quiet, even in the ground state. Even the vacuum has irreducible fluctuations, a kind of minimum jitter that cannot be cooled away. This is not because the vacuum is busy like a boiling liquid, it's because the mathematics forbids perfect stillness, and the prohibition has measurable consequences. A useful visual is a calm surface seen in extreme close-up. From far away it looks glassy, but at high magnification it is textured and restless, with tiny ripples that never quite settle. The vacuum is like that, except the texture is not made of hidden particles. It is made of probability amplitudes, correlations, and constraints that persist even when no detector clicks. The vacuum is calm in the sense that it has no real excitations, but it is not trivial, and it is not featureless. Quantum field theory replaces the idea of a few particles with fields everywhere, filling all of space in the description. Particles are excitations of those fields, and the vacuum is the state with no real excitations. Yet the vacuum still contains zero-point energy, the minimal energy of quantum modes, and that minimum is built into the quantization. Each mode behaves like a harmonic oscillator with a lowest energy that is not zero, because the wave function cannot be squeezed into perfect rest. The vacuum is the baseline of a restless system, not a blank canvas, and the baseline is part of what the theory predicts. The word mode matters because it turns emptiness into a spectrum. Even in a region with no particles, the field can be decomposed into waves of different wavelengths, each with its own allowed quantum states. Quantum theory assigns each wave a set of allowed energies, and the lowest allowed energy is still non-zero, even when no quanta are present. When we add up those contributions across all wavelengths, we run into infinities unless we regulate them. That technical fact is not a loophole, because it is pointing at a deeper mismatch between our descriptions. It tells us the vacuum is not optional, and it tells us our bookkeeping is delicate when we push it toward cosmology. The phrase virtual particles is a metaphor that points to real mathematics. In perturbation theory, internal lines in Feynman diagrams behave like temporary excitations, and they are integrated over rather than observed. They are not directly observable particles flying through space, yet their effects are measurable in precise experiments. They contribute to scattering amplitudes, shift energy levels, and modify forces through quantum corrections. When physicists say virtual particles pop in and out, they are compressing a calculation into imagery. The imagery is memorable, but it can harden into a false literal picture, as if the vacuum were a swarm of tiny objects. A more careful way to say it is that the vacuum has correlations. Even when no particle is present, the fields are not independent at every point, and their fluctuations are statistically linked. They fluctuate in connected ways, and those links can influence how charges interact, even at distances where classical intuition expects emptiness. In quantum electrodynamics, for example, the vacuum becomes polarized around a charge, slightly screening it. That screening changes the effective coupling with distance, a phenomenon measured in high-energy experiments where the strength of electromagnetism runs. So the vacuum is not a passive stage. It is an active participant in the rules of interaction, and it subtly reshapes what we mean by force. A concrete anchor is the Casimir effect, which makes vacuum structure feel less abstract. Put two conducting plates close together, and the allowed electromagnetic modes change, because the boundary conditions restrict which waves can exist between them. The vacuum energy between the plates differs from the vacuum energy outside, not because energy is created, but because the spectrum of allowed fluctuations is altered. The difference produces a small force that can be measured, pulling the plates together. In a lab, this looks like a whisper of attraction where classical intuition expects nothing at all, and the whisper becomes louder as the gap shrinks. The visuals here can be spare and persuasive. Two polished plates hover a hair's breadth apart, and a laser interferometer reads out their separation with unforgiving precision. As the gap narrows, the allowed wavelengths between the plates become restricted, like a guitar string that can only vibrate in certain patterns. Outside the plates, the spectrum of modes is less constrained, and the imbalance shows up as a force. The measurement is difficult because the force is tiny and surfaces are imperfect, with patch potentials and microscopic roughness. Yet the effect persists across careful experiments, and it has become a standard example that empty is not the same as nothing. The Casimir effect is not proof that the vacuum is full of tiny balls of matter. It is evidence that the ground state depends on boundary conditions and field modes, and that those dependencies are physical. It shows that empty space has consequences once quantum fields are taken seriously, even when no particles are present. It also shows that vacuum energy is not just a bookkeeping trick, because changing geometry changes measurable outcomes. The vacuum's properties can be altered by materials, constraints, and shape, and the alterations can be detected without appealing to metaphors. Vacuum fluctuations also appear in other contexts that are less accessible, but conceptually similar. In strong electric fields, the vacuum can produce real particle pairs through the Schwinger effect, turning latent structure into actual electrons and positrons. Here the fluctuations become real particles, drawing energy from the field that was applied, and the vacuum behaves like a medium with a breakdown threshold. In curved spacetime, horizons can turn vacuum correlations into radiation, as in Hawking and Unruh effects. The common theme is that the vacuum is a state with latent structure. Under the right conditions, that structure becomes visible as particles, heat, or force, depending on how the system defines energy. It is worth pausing on what particle even means in these settings, because the word carries more baggage than we admit. In flat spacetime, particles are defined cleanly by symmetries, especially time translation symmetry, which lets us define energy and a stable vacuum. In accelerating frames or near horizons, that symmetry is altered, and the definition of a particle becomes observer-dependent. The Unruh effect captures that twist. An accelerating observer can perceive a thermal bath where an inertial observer sees vacuum. The vacuum did not change as a thing. What changed was the slicing of space-time into time and energy that defines no particles, and the slice is part of the observer's description. At this point, the documentary's hook returns in a new form. We imagined rewinding past atoms, past light, past space and time, as if we were peeling layers from an onion. If the vacuum is already structured, then rewinding to nothing does not land on emptiness. It lands on a state defined by rules, and those rules have measurable consequences, from lab forces to particle spectra. The rewind stops being a journey toward blankness. It becomes a journey toward deeper layers of description, where the background keeps turning into an actor. Vacuum energy also connects to the largest scale mystery in current cosmology. The expansion of the universe is accelerating, as inferred from supernova distances and supported by other probes that cross-check the same conclusion. Supernovae act like calibrated beacons, and their faintness at given redshift suggests the expansion has sped up over time. The cosmic microwave background and large-scale structure add independent support, stitching the same story from different data, like multiple camera angles on the same event. The surprising conclusion is that something like energy of empty space dominates the cosmic budget today, even though it is almost undetectable locally. In the simplest description, acceleration is driven by a cosmological constant. A cosmological constant behaves like a constant energy density of empty space, uniform and persistent, with the same value everywhere we can measure. In Einstein's equations, it appears as an extra term that does not dilute as the universe expands, unlike matter and radiation. That is counterintuitive in everyday terms, because most forms of energy thin out when volume grows. Yet vacuum-like energy stays constant per unit volume, so the total grows with volume as space expands. That growth is not a violation of local conservation. It is a feature of how energy is defined in an expanding geometry, where global conservation is subtle. This is where quantum vacuum physics echoes in the sky. In general relativity, energy density and pressure source gravity, and pressure is not a minor correction. A vacuum-like component has negative pressure, which can drive accelerated expansion. In plain language, it gravitates in a repulsive way on large scales, because the pressure term enters with the right sign in the Friedmann acceleration equation. The same kind of stress energy that can power inflation in the early universe can also appear as dark energy today. The equations treat both as fluids, with equation of state near -1, even if their microphysics may be different. The negative pressure is not an exotic push like a rocket engine, and it is not a force acting through space. It is a property of the vacuum stress-energy tensor, the object that tells space-time how to curve. For ordinary matter, pressure contributes to gravity by adding to the effective energy density, which tends to slow expansion. For vacuum energy, the pressure is negative and equal in magnitude to the energy density, and that combination makes the expansion accelerate rather than slow. It is one of those places where the mathematics is crisp, and the intuition must be rebuilt from the ground up. Yet the connection is not clean, and the mismatch is famous. Naive estimates of vacuum zero-point energy in quantum field theory are enormously larger than the observed dark energy density, by a factor so large it strains comprehension. The cosmological constant problem is not a small discrepancy. It is a sign that we do not understand how vacuum energy gravitates, or how it is regulated when quantum fields meet curved spacetime. Depending on how one cuts off the calculation, the mismatch can be absurdly large. Even after sophisticated treatments, the question remains, why is the vacuum energy so small but not exactly zero? This is not merely a numerical embarrassment. It is a clue that our current frameworks are being combined in a way that misses something essential, perhaps a symmetry or a principle we have not yet found. Quantum field theory is extraordinarily successful in particle physics, and general relativity is extraordinarily successful in gravity. Yet when we ask the vacuum to do double duty, quantum baseline and gravitational source, the fit becomes strained. The vacuum becomes both a candidate explanation and a warning label. It promises a bridge, and it exposes a gap, and the gap sits exactly where origin stories want to stand. So vacuum energy is both a candidate explanation and a warning label. It suggests that emptiness has weight in gravity, and it also suggests our theories are incomplete at a deep level. If we cannot compute the vacuum energy we observe, we should be cautious when using vacuum language to explain creation. The vacuum is powerful, but it is not yet mastered, and the uncertainty is not cosmetic. The same concept that explains a lab-scale force becomes a cosmic-scale puzzle. That is a remarkable continuity, and it is also a caution about overconfident headlines. Still, cosmologists explore proposals where the universe begins as a quantum event. The goal is not to tell a myth with equations, but to replace a classical singularity with a quantum starting condition that stays finite. These ideas are model agnostic at the level we need here. because the documentary is tracking concepts rather than endorsing a single theory. They share a claim that the beginning is not a classical explosion, but a transition in quantum description. The bang becomes a limit of classical extrapolation, not necessarily a physical detonation that happened at a location. One class of ideas uses tunneling language, where a universe can nucleate from a quantum state. The idea borrows from quantum processes where systems cross classically forbidden barriers, and the barrier is defined by the equations of motion. In ordinary tunneling, a particle appears on the other side of a barrier without climbing over it in classical time, and the probability is set by an action. In cosmology, the barrier is a region in the space of geometries where classical spacetime cannot exist. The universe appears as a bubble of spacetime with its own expansion, and the description may use a Euclidean or timeless mathematical segment underneath. Time in such stories can be emergent, arriving only after the transition becomes classical enough to define a clock. The visuals often used are deceptively simple. A small closed bubble forms, like a droplet appearing in supersaturated vapor, and then it expands into darkness. Yet the real object is not a bubble in space. It is a solution in a mathematical configuration space, where different geometries are points, and where distance means difference in curvature and topology. The tunneling is not through physical distance, it is through a barrier in the allowed histories of the universe. That distinction is easy to miss, and it changes what from nothing can mean when the stage itself is what is being produced. Another class uses spontaneous emergence language, where the lowest action configuration includes a small closed universe. The universe is treated as a quantum system with a wave function over geometries, and a beginning is then a boundary condition on that wave function. The beginning is not a moment inside time, but a rule that selects which histories are allowed and how they are weighted. The question becomes which boundary condition is justified, and why, and the answer is not yet settled. Different proposals choose different conditions, and the differences matter for what kinds of universes are likely, including how smooth they start and whether inflation is favoured. The phrase, wave function of the universe, sounds like science fiction, but it is a natural extension of quantum logic. In quantum mechanics, systems are described by wave functions that encode probabilities for outcomes, and those probabilities are tested by repeated measurements. If spacetime itself is part of the system, then the wave function must range over possible geometries, not just over particle positions. That move is conceptually bold, because it treats the stage as a quantum variable rather than a fixed arena. It also creates a new problem, because the usual role of time in quantum theory becomes unclear. If time is part of what is being quantized, what does evolution mean, and what replaces the familiar Schrödinger clock? These proposals attempt to explain why there is an expanding spacetime at all, rather than assuming it as a background. They also attempt to avoid singularities by replacing them with quantum regularity, where quantities remain finite and the classical breakdown is smoothed. They aim to make the beginning less like a point of infinite density, and more like a probabilistic birth of classical geometry. They are not yet confirmed, and they are not all compatible with one another. Some rely on semi-classical approximations, where gravity is treated almost classically while matter is quantized. Others hint at deeper quantum gravitational degrees of freedom that do not look like geometry at all. In every case, the language strains, because we are describing an edge case for our concepts. In many versions, inflation reappears as a natural continuation after nucleation. A small patch with vacuum-like energy can inflate, smoothing and magnifying itself into a large universe, and stretching tiny quantum fluctuations into cosmic structure. That ties back to Chapter 3, where inflation solved puzzles but deferred its own origin. Universe from quantum event ideas try to supply that missing prelude. They attempt to say why an inflating patch existed at all, and why it had the right conditions to start. Inflation becomes the amplifier, while the quantum event becomes the trigger, and the trigger is where nothing is most often invoked. But the word nothing keeps returning, and it keeps changing meaning. A tunneling story often starts from a vacuum state, or from a minimal quantum gravitational state, and then treats that as the absence of everything. That is not philosophical non-being, because it still contains a framework. It contains allowed states, amplitudes, and a notion of probability, and it contains a rule for what counts as minimal. That rule is already a kind of structure, even if it is expressed as an extremum principle. The vacuum in these stories is not a void. It is a specific configuration with constraints, and the constraints are doing the heavy lifting. This is where the documentary's tone becomes deliberately uneasy, because the unease is earned. Universe from nothing headlines often trade on a shift in definitions, and the shift happens quietly. They begin with philosophical nothing in the listener's mind, then substitute quantum vacuum or pre-geometric structure in the mathematics. The result can sound like an explanation while leaving the deepest premise untouched. The audience feels the thrill of a paradox resolved, but the resolution may be semantic rather than ontological. The question is not whether the math is real. The question is what claim the math is actually making, and what it still assumes without comment. The conservation law question is often used to make these stories feel less impossible. In everyday physics, you cannot get something for nothing because energy is conserved, and that rule is tied to time translation symmetry. Conservation works beautifully in many settings, from pendulums to particle collisions, and it feels like a universal lock. In general relativity, defining total energy for the universe is subtle, because gravity is not a force in a fixed space. Energy bookkeeping depends on symmetries and on how space-time behaves at infinity, and the universe may not offer the kind of infinity the definitions want. In a dynamic cosmos with no external outside, the usual global definitions can fail, even when local conservation holds. A popular argument is the free lunch idea, where the total energy of a flat universe might be zero. Positive mass energy in matter and radiation could be balanced by negative gravitational potential energy, so the ledger sums to nothing. If the total is zero, then creation might not violate a simple conservation constraint, at least in a suggestive heuristic sense. This is suggestive, not settled, and it depends on assumptions about global geometry and boundary conditions. It also depends on how one defines gravitational energy, which is notoriously tricky because gravity can be transformed away locally. The appeal of the argument is obvious, because it seems to remove a barrier. The caution is equally obvious, because the barrier may have been misdescribed, or the bookkeeping may not be well defined. Even in a flat Friedman universe, the statement is not a theorem with universal agreement. Gravitational energy is not localized in a coordinate-independent way, and the lack of a unique energy density for gravity is a feature of the theory. Different definitions of energy work in different settings, and cosmology is a hard setting because it is not asymptotically flat. Some definitions require space-time to approach flatness at infinity, which the universe does not obviously do. Others depend on chosen coordinates, which can hide physical meaning behind mathematical convenience. The free lunch argument can motivate, but it cannot close the case, and it cannot substitute for a clear definition of what is being conserved. There is also a deeper issue that conservation does not automatically answer. Even if total energy is zero, a zero total is still a structured condition, and structure is not nothing. It presumes gravity exists, and it presumes a rule for balancing terms, and it presumes that the terms are meaningful. It presumes equations that define what counts as energy in the first place, and those equations are part of the ontology being assumed. A ledger that sums to zero is still a ledger, with categories and accounting rules. So zero is not the same as nothing, and the difference matters at the origin. So the narrative turns to the meta question that refuses to go away. If matter can arise from a vacuum, where did the vacuum come from, and why does it have the fields it has? If space-time can nucleate, where did the quantum framework come from, and why is it describable by amplitudes at all? If laws permit creation, why those laws rather than none, and why these symmetries rather than different ones? These questions are not a retreat into mysticism. They are a recognition of what the models assume as input, and of what they leave outside the frame. In physics, laws are not usually treated as objects that need causes. They are treated as descriptions of regularities, encoded in symmetries and dynamics, and judged by predictive success. Yet when we talk about creation from nothing, laws start acting like ingredients, because they are what makes from and to meaningful. A vacuum with fields and commutators is not empty, and a wave function of the universe is not featureless. Even the choice of what variables exist is already a commitment, and commitments accumulate as we rewind. The deeper we push, the more the laws look like part of the ontology, not merely a human summary. There is a historical echo here, because earlier eras also struggled with what counts as an explanation, and where explanation is allowed to stop. Newton could write equations of motion, yet he refused to speculate about the mechanism of gravity, and his restraint-shaped scientific style. Later, field theory replaced action at a distance with a local medium of influence, and the medium became the new something. Quantum theory then replaced classical fields with quantized ones, and the vacuum became a structured baseline rather than a void. Each step answered one question and exposed another, and the origin question is doing the same thing now. It forces us to ask what we're allowed to take for granted, and what we have merely renamed. Still, the models are not trivial word games, and we should not dismiss them as mere semantics. They show that classical intuition about emptiness is wrong, and they show that nothing happens can be a physically non-trivial statement. They show that quantum theory allows ground states with activity, and that gravity can make global bookkeeping strange. They also show that a beginning might be describable without a prior time, at least in a technical sense. That last point is subtle because it changes what before can mean. If time is emergent, then asking what happened before time may be like asking what is north of the North Pole. The question may be meaningful as poetry, but ill-posed as physics, and the distinction is part of intellectual honesty. But the cost is that nothing becomes a technical term, not an everyday one. Nothing becomes a particular state in a theory, with constraints and degrees of freedom, and with a definition that depends on symmetries. That is a legitimate scientific move, yet it changes the claim, and it changes what the listener should hear. The question becomes whether the theory itself can be explained, or whether it is taken as given. When a physicist says nothing, they may mean no particles in the vacuum state. When a philosopher says nothing, they may mean no being at all. The documentary must keep those meanings from quietly swapping places, because the swap is where confusion is born. This tension mirrors the limit we reached in Chapter 4. Singularities signalled that classical spacetime cannot be extended indefinitely backward, and the signal was mathematical as much as physical. Quantum vacuum stories try to replace the singularity with a quantum starting point, where infinities are avoided and the description remains finite. Yet the quantum starting point still assumes a framework that is not derived inside the story. It assumes a space of possibilities, a rule for amplitudes, and a principle for selecting outcomes, even if the selection is probabilistic. Even if the beginning is probabilistic, the probability calculus has to be there. The mystery does not vanish. It relocates, and it becomes a question about the architecture of the framework. There is also a practical question about evidence, because origin proposals must connect to observables if they are to be physics rather than poetry. Inflation already hides earlier conditions by stretching them away, and it turns many details into universal attractors. A quantum creation event might leave only subtle traces, perhaps in primordial gravitational waves or in specific correlations. Those traces would be encoded in patterns of polarization in the cosmic microwave background, or in statistical fingerprints in large-scale structure. Yet the same expansion that makes the universe smooth can also erase the details of its birth. If those details are washed out, then the origin remains underdetermined by data, and underdetermination changes how confident we can be. That underdetermination is not a failure of imagination. It is a structural feature of the problem, and it is part of why the subject stays mysterious. We're trying to infer a boundary condition from a universe that has undergone enormous dynamical processing, including phase transitions and cosmic expansion. In other areas of physics, we can repeat experiments and vary initial conditions, and the variation teaches us what matters. Cosmology gives us one universe, with one realized history, and we cannot rerun it with a different seed, so the standard of evidence becomes different, and the role of internal consistency becomes larger. A good origin story must fit what we see, but several stories may fit equally well, so we keep two ideas in view at once, without forcing closure. The first is that quantum emptiness is physically real and experimentally constrained, and it behaves like a state with measurable properties. The second is that calling it nothing can be rhetorically convenient but conceptually slippery, because it invites a metaphysical reading the equations do not support. The documentary's central question survives because the ambiguity is not just linguistic. It is built into the structure of our theories, where vacuum is a defined state and nothing is a metaphysical absolute. The gap between them is not a gap we can bridge with a slogan, and it is not a gap we should pretend is closed. Now we return to the rewind image, but we change what we expect to find at the end. We do not necessarily find a void, and we do not necessarily find a first moment that sits cleanly on a timeline. We find a boundary where classical spacetime fails, and beyond it we find candidate quantum descriptions that try to replace the failure with a rule. Those descriptions can be minimal, yet they are not nothing. They are a kind of scaffold, and the scaffold is doing work even when it is described as ground. The camera can linger on that boundary as a shimmering horizon, not in space, but in comprehension, like a limit where the picture turns into equations. This chapter's climax is a controlled confrontation with the smuggled structure. A quantum vacuum contains fields, symmetries, and a definition of energy, and those ingredients are not optional once the theory is chosen. A pre-space-time quantum state contains a rule for amplitudes and a space of possibilities, even if those possibilities are not geometrical in the usual sense. If the universe begins from such a state, then the beginning is not from nothing, but from a deeper something. The something may not look like matter or space, but it is still a set of constraints that could have been otherwise. That is the key reveal, and it is also the key discomfort because it shifts the mystery rather than dissolving it. That does not make the story less mysterious, and it may make it more precise. The mystery shifts from how matter appears to why there is a lawful framework at all, and why it is mathematically stable. It shifts from a dramatic moment to an underlying architecture that quietly governs what can happen. It forces us to ask whether the laws are fundamental, emergent, or selected, and each option opens a different kind of question. If they are fundamental, we ask why those fundamentals. If they are emergent, we ask what they emerge from. If they are selected, we ask what does the selecting and what space of alternatives is being assumed. The questions can be framed in a way that stays scientific, even when they feel philosophical. What counts as a law in physics is often a symmetry principle plus a dynamical rule, and the pairing is what makes prediction possible. Symmetries constrain what can happen, and dynamics tells us how it happens, and the vacuum is defined relative to those constraints. The notion of energy itself depends on symmetry, because energy is tied to time translation, and time may not be fundamental at the beginning. If the vacuum is the lowest energy state, we must ask what sets the energy scale. If the vacuum has fluctuations, we must ask what fixes their correlations and their spectrum. Each answer points back to the framework that was assumed, and the framework is where nothing quietly becomes something. Then we push further, because the chapter cannot end on a word dispute. If nothing still contains law-like structure, perhaps the real origin story lies deeper than quantum field theory on a background. Perhaps it lies in quantum gravity, where space-time and fields emerge together, and where the vacuum is not defined the way we define it now. Perhaps it lies in extra dimensions, or in a landscape of possibilities, or in a cyclic history where beginnings are replaced by transitions. These are not conclusions, and they are not promises. They are signposts indicating where the current language begins to fail, and where the next chapter of physics may need new concepts. The Big Bang remains the earliest chapter we can currently read with confidence, not necessarily the first page of reality. Quantum vacuum stories narrow the gap between nothing and something, yet they also reveal how much structure is required to make the story run. Before the Big Bang may be a physical history, or it may be a question that dissolves when time emerges, and we do not yet know which. Either way, the rewind does not end in a blank screen. It ends in a boundary condition, a set of rules, and a silence that is not empty. The next step is to examine frameworks where the stage itself is built, not assumed, and where nothing is not a metaphor but a problem statement. We have followed the rewind to the boundary where classical spacetime stops behaving, and where our familiar intuitions begin to slip. Chapter 5 showed that nothing in physics still carries structure and rules, because even a vacuum is a state with constraints. Now the tension sharpens into a single demand. If there was a before, it must leave a trace we can test. The Big Bang remains our earliest confident chapter, defined by a hot, expanding plasma whose fingerprints still glow in the microwave sky. When cosmologists say Big Bang, they usually mean the hot early phase, not an absolute creation event. The singularity remains a warning label, not a photographed event, because it marks where classical equations stop giving trustworthy answers. So before the Big Bang becomes a menu of replacements for that warning, each replacement changes what time, causality, and origin even mean. Visually, imagine the cosmic timeline as a bright ribbon. It runs smoothly through nuclear synthesis, recombination, and galaxy formation, then fades into a glare near the Planck era. At that glare, the line does not necessarily end. It may bend, split, or pass through a hidden bridge, depending on which physics governs the boundary. We start with the simplest intuition that still feels physical, because it preserves a single connected history. Expansion could have been preceded by contraction, with the Big Bang as a rebound rather than a first moment. In that picture, the universe did not begin at a point. It passed through a high-density bottleneck where classical equations fail and where quantum corrections could dominate. A bounce is not automatically a cycle with identical repeats, and it is not automatically a cosmic reset. It can be a one-time transition from a prior phase into our expanding branch, with memory partly erased and partly preserved. The key claim is dynamical. Something prevents collapse from reaching infinite curvature, and instead turns contraction into expansion. General relativity alone does not provide that something in ordinary matter conditions, because gravity remains attractive when energy density and pressure are positive. Under classical energy conditions, contraction focuses geodesics and drives incompleteness, which is the technical language behind the singularity theorems. Those theorems, developed by Hawking and Penrose in the late 1960s, do not say a point existed. They say the classical description cannot be extended indefinitely, given certain assumptions about matter and causality. A bounce needs new physics that violates the assumptions behind those theorems, at least effectively. Quantum effects are the usual suspect because quantum stress energy can behave in non-classical ways. Even in ordinary quantum field theory, vacuum fluctuations can produce negative energy densities in limited settings, although they are constrained by quantum inequalities. In quantum gravity, the hope is broader. The geometry itself may resist being squeezed beyond a fundamental scale. Quantum gravity is invoked here as a regulator, not as decoration, because the bounce is only as credible as the mechanism that prevents divergence. Near Planck densities, the smooth manifold picture may be replaced by discrete or emergent geometry, and the metric may become an approximation rather than a definition. If geometry has a smallest meaningful unit, then shrinking to zero becomes an illegal operation. The bounce becomes the theory's way of refusing an unphysical limit. The Planck scale is not just a dramatic number for narration. It is built from constants that define quantum and gravitational strength, and it sets the rough threshold where space-time fluctuations can no longer be ignored. At about 10 Trophkiab meters, the idea of a sharply defined distance may dissolve, and at about 10 Tian 43 seconds, the idea of a classical time tick may lose meaning. A bounce scenario tries to say that the universe approached that regime, but did not fall off a mathematical cliff. Loop quantum cosmology offers an accessible example of this logic, and it has become a standard reference point in popular discussions. It takes the loop quantum gravity idea that geometric quantities are quantized, so that area and volume behave more like energy levels in an atom than like continuous variables. In that framework, area and volume become operators with discrete spectra, and the classical continuum emerges only at scales far larger than the quantum granularity. That discreteness modifies the Friedmann dynamics when densities approach the Planck scale. In the loop picture, the classical Big Bang singularity is replaced by a quantum bridge, which is sometimes described as a quantum bounce. The effective equations include correction terms that act like repulsive gravity at extreme density, not because gravity changes its nature everywhere, but because the quantum geometry changes how curvature responds. Contraction slows, halts, and reverses into expansion. The beginning becomes a turning point in a larger history. To picture it, imagine a graph of the scale factor over time. In standard cosmology, the curve dives towards zero and ends in a vertical wall. In a bounce, the curve narrows to a minimum, then opens again, like a throat that pinches but never closes. The visual is simple, but the physics underneath is demanding, because the theory must stay consistent while the usual approximations fail. This is not a free pass to any story we like, because a bounce is constrained by the universe we actually see. The model must recover ordinary cosmology at low curvature, where general relativity and standard particle physics work extremely well. It must produce a hot Big Bang-like phase with the right thermal history, including nuclear synthesis yields and the timing of recombination. It must also explain why our universe looks so close to flat and so close to Gaussian, because those are quantitative observations, not poetic impressions. Loop quantum cosmology often pairs naturally with inflation, but the relationship is delicate and model-dependent. A bounce can set initial conditions that make inflation more likely in some versions, because the contracting phase can funnel the system into a region of field space that supports accelerated expansion. In other versions, the bounce itself can mimic some inflationary smoothing, at least for limited scales, by altering horizon behavior near the transition. Either way, the question returns with sharper focus. What survives the bounce as an observable imprint? Potential imprints are subtle because later expansion erases memory, and because inflation, if it occurs, is famously good at washing away initial conditions. Still, the bounce can alter the largest scale modes, those that exit and re-enter horizons earliest, and those that suffer the least statistical averaging. It can produce a suppression of power at low multipoles, or specific oscillatory features that look like ringing in the primordial spectrum. It can also generate distinctive non-Gaussian correlations if pre-bounce physics couples modes, because mode coupling is exactly what Gaussianity tries to forbid. The cosmic microwave background becomes a forensic surface in this story. We do not see the bounce directly, but we see a two-dimensional projection of primordial fluctuations, stretched across the sky. On screen, that looks like a mottled sphere of reds and blues, where every patch is a temperature difference of only tens of microkelvin. The differences are tiny, yet they encode the statistics of the earliest accessible perturbations. Tensor modes are a key discriminant, because they probe the energy scale and dynamics in a way scalar density fluctuations cannot. Primordial gravitational waves are ripples of space-time itself, and their amplitude depends on how violently the early universe accelerated or bounced. Some bounce models predict a blue-tilted tensor spectrum, meaning more power at higher frequencies, unlike many slow-roll inflation models that give nearly scale-invariant tensors. Others suppress primordial gravitational waves, because the bounce dynamics can damp tensor production. This sign and scale dependence matter more than the label bounce. Primordial black holes enter as another possible fossil, and they are useful precisely because they turn early universe statistics into late universe objects. If the bounce or pre-bounce phase amplifies curvature perturbations on certain scales, overdensities can collapse after horizon re-entry. That would seed black holes with characteristic mass windows because the mass relates to the horizon size when the perturbation re-enters. Constraints from lensing, CMB distortions, and gravitational wave mergers then become indirect tests, turning modern surveys into probes of ancient dynamics. Gravitational wave backgrounds are the other major channel, and they are often described as a new kind of astronomy. A bounce can generate a stochastic background through amplified vacuum fluctuations, through brief periods of stiff equations of state, or through phase transitions in a pre-bounce sector. The spectrum could peak at frequencies targeted by pulsar timing arrays, space interferometers, or ground-based detectors, which means the same early mechanism might show up in very different instruments. A detection would not automatically prove a bounce, but it could narrow the viable mechanisms by constraining the shape of the spectrum. Yet bounce scenarios face hard problems that keep the mystery sharp, and they are not problems of taste. A contracting universe tends to develop anisotropies that grow faster than ordinary matter, because sheer energy density scales roughly as 8-6 in simple treatments. Without a smoothing mechanism, contraction becomes chaotic and inhomogeneous, a behavior related to the Belinsky, Kalatnikov-Lifshitz picture of approach to singularities. A successful bounce must control that instability, or else it produces a universe unlike ours. This is where a second family of before ideas enters, with a different strategy. Instead of relying on quantum discreteness alone, it engineers a special kind of contraction that behaves almost like a cosmic ironing process. The ekprotic scenario uses a slow contraction with a very stiff effective equation of state, meaning pressure is large compared to energy density. That stiff component suppresses anisotropies and smooths the universe before the bounce, because it can dominate over shear as the scale factor shrinks. Ekpyrotic models are often motivated by higher dimensional physics, and that motivation has a history in string-inspired cosmology. They picture our visible universe as a three-dimensional brain embedded in a higher dimensional bulk, a setting that echoes ideas from brain-world scenarios of the late 1990s and early 2000s. Another brain exists nearby in the extra dimension, separated by a small distance that can change over time. Their relative motion becomes the clock that drives the pre-Big Bang phase. In the simplest framing, the hot Big Bang is not an initial explosion in empty space. It is the aftermath of a brain interaction, often described as a collision, though the word collision is a metaphor for a high-energy transition in the underlying theory. The collision converts kinetic and potential energy into radiation, and matter on the brain. Reheating becomes a geometric event rather than a field rolling down a potential, and the heat of the early universe becomes a consequence of brain dynamics. For visuals, picture two vast, dimly lit sheets floating in a dark, higher dimensional volume. They drift toward each other, not like objects in ordinary space, but like entire worlds approaching along an unseen axis. As they near, the scene brightens at the interface, and a flash of radiation spreads across the brain like a sunrise racing along a horizon. The camera then dives into the familiar hot plasma, connecting the abstract geometry to the standard Big Bang narrative. This brain picture changes what before means without removing it, because time can extend through the pre-collision phase in the higher dimensional description. The singularity is reinterpreted as a breakdown of the four-dimensional effective theory, not necessarily of the deeper model. The deeper theory claims to remain finite through the transition, although making that claim precise is one of the technical challenges. In other words, the edge may be an artifact of using the wrong variables. Ekpyrotic scenarios must also reproduce the observed spectrum of perturbations, and this is where the comparison to inflation becomes sharp. Inflation generates nearly scale-invariant curvature perturbations from quantum fluctuations during accelerated expansion, and it does so with a mechanism that is mathematically clean in many models. Ekprosis must generate similar statistics during contraction, often using multiple fields or entropic perturbations that live orthogonally to the background trajectory. The conversion from entropy to curvature perturbations becomes a central mechanism because the observable pattern is curvature, not entropy. This is where testability becomes sharp, because the mechanisms differ in their fingerprints even when they match the same headline numbers. Ekpyrotic models often predict distinctive non-Gaussianity, sometimes of the local type, because the conversion process can introduce nonlinearities. They can also predict a strongly suppressed primordial tensor signal, since slow contraction does not generically excite gravitational waves the way rapid expansion can. If future CMB polarization detects a large tensor-to-scalar ratio, many ekpyrotic versions would be strained. But non-detection of tensors does not automatically favour ekpyrosis, and this is where careful narration matters. Many inflation models also predict small tensors, either because the inflationary energy scale is low, or because the potential is shaped to reduce tensor production. The discriminant becomes a pattern across observables, not a single number. Non-Gaussian shapes, running of the spectral index, and isocurvature constraints all become part of the verdict, and they must agree with each other. Brain-inspired pictures also face their own consistency demands, which can be as unforgiving as observational constraints. The higher dimensional setup must be stable and well-defined, and it must avoid pathologies like uncontrolled instabilities in the extra dimension. The collision must avoid producing unacceptable relics or singular behavior, because a cure that reintroduces infinities has not solved the problem. The scenario must explain why the extra dimensions behave the way they do today, including why they are hidden from low-energy experiments. Without that, the before becomes a placeholder rather than a mechanism. So far, bounces and brains keep a recognizable earlier and later, and they preserve a kind of cosmic history that continues through the Big Bang. They offer continuity, even if the continuity passes through a quantum or higher dimensional bottleneck. The third frontier breaks that intuition more radically. It suggests that our Big Bang is not the beginning even locally, but one event among many. Eternal inflation begins with an idea we already met in Chapter 3, but here it is pushed to its most unsettling implication. Inflation is an accelerated expansion driven by vacuum-like energy, and it can be modelled as a scalar field perched on a potential landscape. In many models, quantum fluctuations of the inflaton field can keep inflation going in some regions, even as it ends in others, because the field jitters upward in energy in rare patches. Inflation then becomes future eternal on the larger scales, even while it ends locally. In that picture, the Big Bang is not a unique global event. It is a local reheating event inside a pocket universe, also called a bubble, embedded in an inflating background. Each bubble forms when inflation ends locally, and energy converts into hot radiation, creating conditions that look like a Big Bang to observers inside. Inside each bubble, observers see a hot Big Bang-like beginning, complete with a last scattering surface and a finite observable horizon. The global structure is different from the local story, and the documentary needs the viewer to feel that difference. Globally, the inflating background keeps expanding and spawning new bubbles, like a foam that never finishes forming. Locally, each bubble has its own cosmic time and its own horizon, and its own causal boundaries that limit what can ever be observed. The question shifts from what began the Big Bang to what is the multiverse doing overall, and whether that overall description is even the right object for science. This shift feels like progress and evasion at the same time, and that ambiguity is part of the chapter's mood. It replaces a singular start with an ongoing process, which sounds like an explanatory gain. It also pushes the origin question outward, because the inflating background becomes the new thing that demands an origin. What started the inflating background, and did it have a beginning at all? Here the past incompleteness results return with force, and they act like a brake on overconfident storytelling. Some inflationary spacetimes can be future eternal yet still past incomplete under broad conditions, as argued in results associated with Borde, Guth and Vilenkin. That suggests eternal inflation does not automatically remove the need for earlier physics. It may create many beginnings while still requiring a deeper boundary, which could be quantum, geometric, or something even more abstract. Eternal inflation also intensifies the meaning of nothing, because the background is not an empty stage. If bubbles nucleate from a metastable vacuum, then the background is a quantum state with energy, fields, and decay channels, and it has dynamics governed by quantum tunneling. Our universe becomes one outcome among many, not a creation from absolute absence. The word vacuum sounds like nothing, yet in modern physics it is a structured medium with measurable effects. The multiverse picture can also connect to string theory's landscape idea, which suggests there may be many metastable vacua with different low-energy physics. If that is true, then different bubbles can realize different constants and particle spectra, and the same underlying theory could produce a vast variety of effective universes. The anthropic argument enters as a controversial tool, not because it is logically impossible, but because it changes what explanation means. It says we observe conditions compatible with observers because incompatible regions have no observers, and therefore no one to ask the question. This is where the documentary's climax becomes a methodological confrontation, not just a tour of exotic ideas. Cosmology is not only about what is imaginable, it is about what is predictive under uncertainty, and about what can be ruled out by data rather than accommodated by narrative. A multiverse can explain why some parameters look finely tuned, but it can also weaken sharp predictions, because somewhere becomes a refuge for almost any outcome. The measure problem is the technical name for that weakness, and it is more than a philosophical complaint. In eternal inflation, infinitely many bubbles can form, and many events occur infinitely often, because the process does not end globally. To make probabilities, you must regulate the infinities with a cutoff or a measure, and then take a limit that is hoped to be meaningful. Different measures can yield different predictions, even when the underlying dynamics is the same, which means the framework risks ambiguity at its core. This is not a minor bookkeeping choice, because it can change which kinds of universes are typical in the regulated ensemble. It can affect predictions for the cosmological constant, for curvature, and for the distribution of inflationary histories. If the probabilities depend on arbitrary choices, the framework risks losing scientific bite, because different researchers can get different answers from the same starting assumptions. The question becomes uncomfortable. Are we learning about nature or about our chosen method of counting? The measure problem also exposes a deeper issue about what counts as an observer and what counts as a sample, and those words hide technical landmines. We observe one universe from one location in one cosmic time, and our data are conditioned on our existence. Eternal inflation asks us to reason about an ensemble we cannot directly access, using indirect inferences and assumptions about typicality. The inference becomes entangled with selection effects and with definitions of what it means to be randomly chosen from an infinite set. Yet the multiverse is not automatically untestable, and the chapter must keep that door open without pretending it is easy. Some signatures could arise if our bubble collided with another bubble in the past, because bubble walls carry energy and can perturb the reheating surface. Such collisions could leave localized features in the CMB temperature map or polarization patterns, perhaps as circular or disk-like anomalies. They could also imprint a preferred direction, though foregrounds, systematics, and statistics complicate claims, and cosmic variance sets a hard limit. Another possible signature is residual spatial curvature, which is one of the few global geometric properties we can attempt to measure. Many inflation models drive curvature extremely close to zero, but not exactly, and the remaining value depends on the duration and details of inflation. Some eternal inflation scenarios make small negative curvature more plausible in typical bubbles, because bubble interiors can resemble open universes. A robust detection of curvature would be a major clue, though it would not uniquely select a multiverse, because other mechanisms can also leave curvature. Topological defects are another channel, and they link high-energy symmetry breaking to observable relics. Bubble nucleation and symmetry breaking can produce cosmic strings or other defects, depending on the field content and the pattern of symmetry breaking. Strings would leave line-like discontinuities in CMB maps and a characteristic gravitational wave background, with a spectrum shaped by string loops. Current limits already constrain many string tensions, but future surveys could push further, turning absence into information. Across bounces, branes, and multiverses, the same question keeps returning, and it is the spine of the chapter. What would count as evidence rather than after-the-fact storytelling? The answer is not one magic observation. It is a network of constraints that converge on a mechanism where each dataset limits the freedom to improvise. Non-Gaussianity is one of the sharpest tools because it encodes interactions in the early universe, and interactions leave statistical scars. Inflation in its simplest slow-roll form predicts nearly Gaussian fluctuations, because the inflaton behaves almost like a free field on an expanding background. Alternatives often generate larger or differently shaped non-Gaussianity, because they rely on multiple fields, conversions, or non-trivial dynamics during contraction or transitions. Measurements from Planck already limit many possibilities, and future surveys can tighten those limits by mapping more modes and reducing noise. Tensor modes remain a central prize because they probe the energy scale of the earliest dynamics, with fewer model-dependent conversions. A detection of primordial B modes with the right frequency dependence would strongly support an inflationary origin of perturbations, because it would indicate a primordial gravitational wave background. It would also constrain many bounce and ekpyrotic models that suppress tensors, forcing them into narrower corners of parameter space. Continued non-detection keeps many models alive, but it shifts the plausible parameter space and raises the bar for high-scale inflation. Specific CMB anomalies sit in a grey zone between clue and coincidence, and the chapter should let that ambiguity breathe. Lowell power suppression, hemispherical asymmetry, and alignments have been discussed for decades, and they remain intriguing partly because they are hard to interpret. A bounce could naturally affect the larger scales, because those modes are most sensitive to pre-inflationary history and to horizon behaviour near a transition. But cosmic variance limits how decisive those anomalies can ever be, because we only have one sky and one set of large-scale modes. Primordial black holes provide a different kind of test, because they connect early perturbations to later astrophysical consequences in a way that is hard to hide. Overproduction is easy and already constrained, since too many primordial black holes would distort the CMB, disrupt structure formation, or overproduce merger events. Underproduction is uninformative, because many models produce none and remain viable. The useful regime is a predicted mass spectrum tied to a specific early universe feature, where the same mechanism predicts both an enhancement and its scale. Gravitational wave backgrounds provide a complementary fossil record, and they are especially valuable because they can probe eras far earlier than recombination. Inflation predicts a broad spectrum of tensor fluctuations, though amplitude varies widely by model and can be too small to detect. Bounces and phase transitions can produce peaked spectra at detector-specific frequencies, which means the signal could be concentrated in bands accessible to particular experiments. The shape of the spectrum across bands becomes the discriminant, because different mechanisms produce different slopes, peaks, and cutoffs. Large-scale structure surveys extend the CMB's reach by mapping three-dimensional statistics, turning the universe into a volume rather than a surface. They can constrain primordial non-Gaussianity through scale-dependent bias, which is a subtle but powerful effect on how galaxies trace matter. They can test features in the power spectrum that might originate in a bounce or in a non-standard reheating, because features propagate into clustering patterns. They can also cross-check inflationary consistency relations if tensors are detected, linking scalar and tensor statistics. But testability is not only about instruments, and it is not only about collecting more data. It is about whether a framework makes risky predictions that could have been wrong, rather than flexible stories that can be tuned after the fact. A model that can fit any outcome by adjusting hidden parameters is not explanatory, even if it is mathematically elegant. The early universe frontier is full of flexibility, and flexibility is both a strength and a trap, because it can shelter ideas from refutation. This is why the chapter's mood stays mysterious rather than triumphant, even as the ideas become grand. Each before scenario is an attempt to keep physics continuous across the boundary, where our equations broke, and each offers a different kind of continuity. Each scenario also risks becoming a story that lives safely beyond observation, protected by the very remoteness that makes it alluring. The boundary between physics and metaphysics is not a location, it is a standard of evidence. We can now state the dilemma cleanly, and the viewer should feel the simplicity beneath the complexity. If the Big Bang singularity is not physical, then something replaces it, because nature does not tolerate infinities as literal events. A bounce replaces it with earlier time and a dynamical turnaround. A brain collision replaces it with higher dimensional dynamics and a transfer of energy between geometric objects. Eternal inflation replaces it with a global process that generates many local beginnings, each with its own apparent origin. Each replacement changes the meaning of beginning in a different way, and each changes what we mean by explanation. A bounce makes the beginning a turnaround, where time extends through the bottleneck. A brain story makes the beginning a transfer of energy between worlds, where the four-dimensional description is a shadow. Eternal inflation makes the beginning a local perspective inside an endless background, where the word the Big Bang quietly loses its privilege. Yet all three face the same ultimate question, and it is not a rhetorical flourish. Do they reduce mystery, or do they move it to a deeper layer? If a bounce occurred, what set the pre-bounce conditions and why that state rather than another? If brains collided, why those brains and why that motion through the extra dimension? If inflation is eternal, what started the inflating state and why it exists at all? The documentary's central question returns with sharper edges, because language becomes a kind of experimental apparatus here. When we say nothing, do we mean a vacuum that can decay, a pre-geometric quantum state, or a true absence of space-time? When we say before, do we mean earlier time, a different dimension, or a question that dissolves because time emerges? The words are small, but the commitments are enormous, and the commitments guide what counts as a legitimate answer. This chapter is the climax because it forces a choice about scientific responsibility, and because it reveals how cosmology is constrained by method as much as by math. We can explore bold ideas, but we must separate what is mathematically consistent from what is empirically anchored, because consistency is not the same as truth. We can accept that the universe may hide its earliest moments, but we cannot let hiddenness become an excuse for unfalsifiability, because then the boundary of knowledge becomes a boundary of discipline. So we end with a disciplined kind of wonder, the kind that does not confuse mystery with permission. The universe might have bounced, or collided, or budded off from an inflating sea, and each possibility reshapes the story of origin. It might also have begun in a way that makes before the wrong grammar, because time itself could be emergent from deeper relations. The evidence we have is real, and the evidence we lack is the point. After touring these frontiers, we return to what science can say without overreach, and that return is part of the narrative arc. We know the universe began in heat and expansion within our observable past, and we can trace that history with remarkable precision. We suspect quantum gravity reshapes the earliest boundary, because our best theories demand it, and because singularities signal missing physics. We do not yet know whether before is history, multiverse structure, or a limit of time itself. The next chapter will tighten the lens on that responsibility, because the temptation to overclaim grows with the grandeur of the questions. It will separate robust inference from seductive extrapolation, and it will ask where confidence is earned rather than assumed. It will ask which mysteries are narrowing, and which may remain permanently beyond the horizon of testable science, even as our instruments sharpen and our theories mature. We return to the central question with the rewind still running in our minds, like film spooling backward through a projector. If the Big Bang began our observable universe, what started it, and what can before even mean? The first answer is also the most disciplined one, and it is less dramatic than people expect. The Big Bang is not a claim about absolute creation, but a well-tested description of an early hot, dense, expanding state, and its aftermath. When we say Big Bang in modern cosmology, we mean a thermal history we can reconstruct from data. We mean expansion, cooling, and changing particle species as the universe dilutes and evolves, with each transition leaving a faint but measurable trace. That distinction matters because the phrase the Big Bang often smuggles in a firework image. In the equations, it is closer to a changing geometry, space itself stretching, while matter and radiation respond according to well-defined microphysics. The most solid evidence is not one clue, but convergence across independent witnesses that do not share the same weaknesses. Expansion history, the cosmic microwave background, primordial nucleosynthesis, and structure formation agree on one coherent framework, even when measured by different instruments and different teams. Start with expansion, because it is the backbone of the rewind and the simplest thing to visualize. Galaxies are redshifted in a way consistent with metric expansion, not debris flying through static space, and that difference is encoded in how distances, times, and wavelengths scale together. Historically, this was not an instant revelation, and it arrived in pieces across the early 20th century. Einstein's general relativity made dynamical space possible, Lemaitre connected it to redshifts, and Hubble's distance ladder turned the idea into a quantitative relation. The Hubble-Lemaitre relation ties distance to recession in a way that points backward with mathematical insistence. Run the equations in reverse, and the universe was denser, hotter, and more uniform, with the scale factor shrinking toward a regime where ordinary intuition stops working. In visuals, the expansion is not an explosion from a center, but a swelling grid where every square grows. The light from distant galaxies is stretched along with space, each photon arriving longer in wavelength, as if the universe itself has pulled the color toward red. Then the CMB locks the story to a specific physical surface, and it does so with extraordinary precision. It is a near-perfect blackbody afterglow from recombination, when the plasma became transparent about 380,000 years in, at a temperature near 3000 Kelvin. Before that moment, electrons and protons scattered photons so efficiently that the universe behaved like an opaque fog. As it cooled, neutral atoms formed, scattering plummeted, and photons began to free stream. Those same photons now fill the sky as microwaves at 2.7 Kelvin. The blackbody spectrum is not just pretty, it is diagnostic, because it implies thermal equilibrium in the early plasma. Deviations would have signaled exotic energy injection or missing physics, yet the spectrum is so clean that it constrains entire classes of alternatives. Its tiny anisotropies are not noise, but encoded initial conditions written in temperature differences of tens of microkelvin. Acoustic peaks and polarization patterns constrain curvature, baryon density, dark matter content, and the statistics of primordial fluctuations, like a fingerprint that matches only a narrow family of histories. Those peaks come from sound waves in the primordial plasma, where radiation pressure fought gravity in a rhythmic tug-of-war. The spacing and heights of the peaks record the speed of sound, the matter content, and the geometry of space, plain language clues hidden inside a subtle pattern. Polarization adds another layer, because it remembers the direction of scattering as well as the intensity of light. E-modes trace density fluctuations with high confidence, while the more elusive B-modes could carry the imprint of primordial gravitational waves if they exist. Nucleosynthesis anchors the first minutes with different physics and different systematics, which makes it a powerful cross-check. Light element abundances match a hot early plasma, where protons and neutrons froze out, then fused into helium and deuterium as the universe expanded and cooled. In that early furnace, temperature and density fell so quickly that nuclear reactions raced against the clock. Neutrons decayed as they waited, so the final helium fraction is a kind of cosmic stopwatch, sensitive to the expansion rate and the number of relativistic species. Deuterium is the tightest baryometer, and it agrees with the CMB's inferred baryon density to impressive accuracy. That agreement is a rare kind of cross-check, because it links minutes to hundreds of thousands of years, and it links nuclear physics in stars' ancestors to photons in our telescopes. Structure formation extends the same initial seeds into the late universe, where we can map them in 3 dimensions. The cosmic web, galaxy clustering, and lensing patterns trace growth from small primordial perturbations under gravity, with dark matter providing the scaffolding that ordinary matter later decorates. In images, the web looks like frost spreading across glass, with filaments feeding bright nodes of galaxies, That pattern is not accidental because gravity amplifies tiny overdensities, while cosmic expansion slows the growth, an ongoing competition that depends on the universe's contents. Taken together, these are the parts of the beginning we can touch, and they are surprisingly concrete. They tell us the universe was once hot, dense, and expanding, and that it carried small, nearly Gaussian fluctuations that later became everything we see. Now we state the boundary without drama, because the boundary is methodological, not emotional. If we push earlier than the hot Big Bang description, our equations demand both quantum theory and gravity at once, and we do not yet have a complete tested union of the two. Classical general relativity extrapolated backward yields a singularity, but that is not a filmed event in any ordinary sense. It is geodesic in completeness and divergent curvature, which signals breakdown of the classical model, much like infinite density signals that a fluid approximation has been pushed beyond its domain. The word singularity can mislead, because it sounds like a place where physics becomes magical. In practice, it is a warning light on the dashboard, an indication that the variables we chose are no longer the right ones for the regime we are entering. The Planck era is where the real breaks in a technical sense, and the numbers make the point stark. At about 10^43 seconds, the notion of smooth spacetime is expected to fail, and time may not be a usable parameter in the way our equations assume. At those energies, quantum fluctuations of geometry itself should be significant, not merely fluctuations of fields on a fixed background. The Planck length is so small that familiar concepts like distance and duration may become statistical or emergent, rather than fundamental. This is where inflation enters as a powerful, incomplete bridge, because it reaches backward without claiming to be the final origin. Inflation explains why the CMB is so uniform across causally disconnected regions, and why spatial curvature is so close to zero, as if the universe has been stretched flat. It also addresses the absence of heavy relics predicted by some high-energy theories, because rapid expansion can dilute unwanted species. In the simplest versions, inflation is driven by a field whose potential energy behaves like a temporary vacuum energy, producing accelerated expansion. Inflation also explains why quantum fluctuations became the seeds of galaxies, which is one of its most striking conceptual moves. It stretches microscopic perturbations beyond the Hubble radius, then returns them later as classical density variations, leaving a nearly scale-invariant spectrum that matches what we infer. That story is subtle because it turns quantum uncertainty into classical structure through expansion and decoherence. The fluctuations are not little balls of matter, but variations in field values and curvature, later translated into overdense and underdense regions when the universe becomes matter-dominated. Yet inflation does not settle the origin question. It sharpens it with new precision. What started inflation? What selected its field and potential? And why did an inflating patch exist at all, rather than a different initial condition that never inflated? The key discriminant remains what we have not yet seen, and the absence is as informative as the presence. Primordial gravitational waves would imprint B-mode polarization, but foregrounds and instrumental limits keep the verdict open, because dust and lensing can mimic the same curling pattern. A detection would point to a high inflationary energy scale and narrow the model space, turning speculation into a constrained inference. Continued non-detection still allows inflation, but pushes it toward lower scales and more constrained dynamics, where some simple potentials become less plausible. Then we push further, because the chapter cannot end at inflation's edge. Even if inflation is real, even if inflation happened, it may be past incomplete, which suggests earlier physics or a deeper boundary, and it forces us to ask whether any beginning can be made eternal. This is where the Before Big Bang menu from the previous chapter becomes a single theme, rather than a collection of fantasies. Bounces, brains, and eternal inflation are not answers, but structured ways to replace the singularity warning, each with calculational frameworks and potential observational consequences. A bounce keeps a continuous history by turning contraction into expansion, like a cosmological inhale followed by an exhale. It requires new physics that effectively violates classical assumptions, often through quantum gravity corrections or exotic stress energy, that changes how gravity focuses geodesics. In many bounce models, the challenge is not only achieving the bounce, but preserving the right kind of perturbations. The universe must pass through the high-density phase without generating instabilities that would spoil the near-Gaussian, nearly scale-invariant pattern we observe. Brain and ekpyrotic scenarios relocate the beginning into higher dimensional dynamics, shifting the story's stage rather than its plot. They aim to smooth the prehistory through stiff contraction, then reheat through a transition that looks like a bang, producing a hot plasma without a classical singularity. Eternal inflation reframes the Big Bang as local rather than global, which changes the emotional meaning of the beginning. Our hot beginning becomes one reheating event inside a larger inflating background that may spawn many pocket universes, each with its own thermal history and perhaps its own effective constants. Each option changes what before means, and each inherits a deeper origin question that refuses to disappear. If there is a bounce, what set the pre-bounce state? If there is a multiverse, what started the inflating background, and why does it exist instead of not? So we return to the hardest word in the title of the whole documentary, because it is where language and physics collide. Nothing in physics is rarely absolute non-being, because physics begins by assuming a framework of states and rules, even when it tries to minimize them. In everyday language, nothing means no things. No space, no time, no laws, and no potential for change. In physics, nothing usually means no particles in a vacuum state, or no classical space-time geometry, which is already a much more structured concept. A quantum vacuum is not empty in the philosophical sense, and experiments have taught us to take that seriously. It is the ground state of fields with correlations, fluctuations, and symmetries that can produce measurable effects, such as shifts in energy levels and forces between conductors. Even the more radical, no classical space-time is not automatically lawless, and that is the part that often surprises people. Many proposals still assume quantum rules, a space of possibilities, and a principle that selects or weights histories, even if those histories are not written in ordinary time. So, something from nothing often hides a substitution that is easy to miss in conversation. The listener imagines absolute absence, while the equations describe a structured quantum state, or a pre-geometric regime with constraints that function like laws. That does not make the work meaningless, it makes it precise, and precision is the price of progress. The real question becomes whether the assumed rules are fundamental, emergent, or contingent, and how we could ever tell from observations inside one universe. Now we confront the grammar of before with the same discipline, because grammar can encode a false assumption. If time is part of the universe, then before time may be ill-posed, not merely unknown, and the discomfort we feel may be a clue rather than a failure. Quantum gravity raises the problem of time in a technical way, not as a poetic puzzle. If there is no external clock, then evolution may be relational, and time may emerge from correlations in a semi-classical limit, when geometry becomes approximately smooth. In that case, asking what happened before the Big Bang can resemble asking what is north of the North Pole. The question can be meaningful as metaphor, but not as a physical parameter, because the coordinate we are trying to extend may simply end, but we do not get to declare victory by dissolving the question, because the universe still has an arrow. If time emerges, we still must explain the conditions under which a classical arrow of time appears, and why it is stable against the microscopic reversibility of many laws. So we separate what we know from what we hope to learn, and that separation is part of scientific honesty. We know the hot Big Bang framework works from nucleosynthesis onward, and it fits precision data with a small set of parameters that repeatedly survive new measurements. We do not know the physics of the Planck era, and we do not know whether inflation is fundamental or effective, like a useful approximation. We do not know whether before is history, multiverse structure, or meaningless, and we do not yet know which observations could decisively choose. This is where uncertainty becomes a feature, not a failure, because it tells us where information is missing. Cosmology is constrained by one universe and one sky, so evidence must come from faint patterns and statistical consistency, not from rerunning the experiment under new initial conditions. The path forward is not one heroic experiment, but a coordinated attack on early universe signatures across multiple messengers. We look for new information in polarization, gravitational waves, and three-dimensional maps of structure, because each probe sees the same early physics through different distortions. Next-generation CMB polarization surveys aim to separate primordial B modes from dust and lensing, which requires exquisite control of systematics. They also refine constraints on non-Gaussianity, isocurvature, and any departures from simple inflation, turning the sky into a laboratory for high-energy field theory. In visuals, this work looks almost surgical, with maps being cleaned layer by layer. Foreground templates peel away the Milky Way's glow, then lensing is reconstructed and subtracted, until any residual curl pattern can be tested against the physics of the earliest moments. Gravitational wave observatories open a second fossil record, one that does not rely on light at all. Space interferometers, pulsar timing arrays, and future ground detectors can search for stochastic backgrounds from inflation, bounces, or phase transitions, each producing a characteristic spectrum across frequency bands. Large-scale structure surveys add volume and leverage because they sample many more modes than the CMB's two-dimensional surface. Galaxy clustering, weak lensing, and 21-centimeter mapping can constrain primordial statistics across more modes than the CMB alone, and they can test how initial conditions evolved under gravity. Theory work is the fourth instrument, because interpretation is part of measurement and ambiguity can masquerade as discovery. Quantum gravity, effective field theory of inflation, and alternatives must produce calculable, risky predictions, and they must connect to observables without adjustable stories that fit anything. We should expect partial answers rather than a single final explanation, and that expectation is not pessimism. The early universe may be an attractor that erases details, which means several deep stories can lead to similar observable outcomes, leaving us to distinguish them with subtle signatures. So we close with a reframing that respects both wonder and limits, and it keeps the mystery in the right place. The Big Bang is the earliest chapter we can read with confidence, not necessarily the first page of reality, and the difference between those two statements is where modern cosmology lives. The beginning we can touch is heat, expansion, and a sky full of faint light, measured with instruments that turn microwaves into maps. What began that beginning remains open, because nothing, law, and time are still under negotiation, and our best theories disagree on which concepts are primary. If the universe had to begin, then the origin is a physical event waiting for sharper tools, and the sky may still carry its signature. If the universe did not have to begin, then the deepest mystery is why our history has a readable start, with a thermal past that can be reconstructed at all. Either way, cosmology is the art of extracting a beginning from leftovers, from photons, elements, and patterns in the distribution of matter. We learn what the universe did, then we learn what questions the universe allows us to ask, and which questions collapse under their own assumptions. And the rewind stops where it must, not in darkness, but at the edge of definition, where our variables lose their meaning. Beyond that edge, we do not yet know what before means, and that is the honest ending. We rewound the cosmos like a film, and the evidence kept matching frame after frame, redshifts tracing metric expansion, light elements counting the first minutes, and the microwave afterglow preserving the universe at 380,000 years. Inflation, if it happened, explains why the sky looks so uniformly warmed and so nearly flat, while quantum fluctuations become the faint seeds of every galaxy and void we see today. Yet as we approach the first instance, our best equations stop behaving like a map and start acting like a warning label, because general relativity and quantum physics both demand to speak at once. That real break is what the singularity really is, not a place we can visit, but a sign that the classical story runs out of trustworthy frames near the Planck scale. In that gap, nothing splits into competing meanings: philosophical non-being, a quantum vacuum rich with structure, or a pre-geometric regime where even space and time are not yet classical concepts. And the proposed replacements for the missing frames, bounces, brains, tunneling beginnings, or eternal inflation's branching multiverse, only earn their place if they leave risky fingerprints in polarization patterns, non-Gaussian correlations, relic waves, or subtle large-scale anomalies. Across every chapter, one theme kept returning: cosmology is not myth-making, it is forensics under strict rules, where independent witnesses must agree, and where beautiful ideas must pay rent in measurable consequences. The Big Bang, in that sense, is not a claim that everything came from absolute nothing. It is the name for a hot, dense, expanding early chapter that our data can still read. What comes earlier, if anything comes earlier at all, is where physics is still learning what questions remain meaningful when the stage itself is being built. So when we rewind reality far enough that the universe seems to lose its stage, the honest answer is that before may be a real history we have not decoded, or it may be a word that stops working when time emerges. And nothing may not be empty at all, but a structured quantum ground state, or simply the label we attach to the edge of what our current theories can say without contradiction? The beginning we can touch is a universe born into heat and expansion, with faint quantum whispers stretched across the sky, still visible in the afterglow. The deeper beginning, what began that beginning, remains mysterious, but not infinite, because every new measurement turns the darkness into a smaller, sharper question. If you want to follow the story as it becomes testable,